Okay. Δουλεύει, είναι online. Ωραία, πότε ξεκινάμε? Okay. Good morning, everyone. We're very happy to have Professor Aristomenis Aristos Donos from Durham University here, who's going to talk to us about nearly critical superfluids and holography. Thank you very much.
So I would like to thank the organizers for this nice workshop that happens every year, and especially this year that they gave me the opportunity to talk about some work that I had been doing together with Christiana Pantelidou, I guess she's not here, and also with Polidoros Kailidis, who is a postdoc at Durham University. Right, so how is this going to look like? So in the beginning, I will give you an introduction and some generalities and motivate the problem that I would like to discuss about nearly critical superfluids. And then we will start discussing about near criticality in field theory constructions that existed, in the past, from the 70s, basically, and the 60s. And this is why I call it an n less than infinity. And very quickly, we will take n to infinity, and we will start discussing holography, where things will simplify a lot in many ways, and we will actually be able to do some microscopic calculations and extract information from holography. And then I will conclude. All right, so what is the motivation behind looking at these effective field theories? Well, what happens often at strong coupling is that you don't have quasi-particles. Quasi-particles, I mean, the definition for me would be excitations that are long-lived. And because of strong interactions, most of the excitations will die off quickly. But if you are interested in asking questions about, long wavelengths, basically wavelengths which are much bigger than a typical microscopic distance in your theory, then the relevant question that you need to ask is about the dynamics of conserved charges and Golson modes in the case that you have symmetry breaking. Okay, so these are the lightest modes. These will be the long-lived modes in your system, and they will dominate the dynamics as you approach thermalization at finite temperature, especially. Okay, now today I want to go. In the case that I do have a phase transition, I want to go very close to the phase transition, right, to the critical point, where there is a correlation length that shows up in the theory. And as I approach the critical point, this correlation length blows up, it goes to infinity, and it washes away any scale in the system, right? So at exactly a critical point, you could expect to get conformal invariance, or scale invariance, at least. All scales just get washed away from the system. So you would expect to see universality close to critical points, and indeed you see universality. And I want to ask, what can we learn actually from holography about the dynamics close to such a critical point? Okay, so let me give you the setup. How am I thinking about these systems? So we'll be looking at relativistic theories, okay? Relativistic field theories with a global U1. I want to consider symmetry breaking, so I do need some kind of global symmetry. We will put these theories at finite temperature and chemical potential. And there is some kind of charged operator which transforms non-trivially under this U1. And below a critical temperature, or as I'm varying other parameters in the system, for some reason, this operator wants to take a non-trivial vacuum expectation value. Right? So, and that will break spontaneously the U1 of the system. And I also want to introduce a mu, which is an external Maxwell field, right? So I'm fixing externally this to the system. I want to talk to the system somehow. I want to interact with it. And I'm introducing external electromagnetic fields. So for me, this will not be a dynamical player. Okay, it will just be an external source. And I'm also imagining that I can introduce scalar sources that couple to this operator O psi, and which can actually explicitly break the U1 symmetry. We will not do much with it, okay? I'm just introducing it to tell you that if I take derivatives of some partition function later with respect to that source, I can compute the verbs of this operator. Okay, so in an ideal world, you would take this theory, you would be able to compute the partition function at finite temperature, chemical potential, and for general metric background, and for general external Maxwell field configurations. And you can then compute the generating function by taking a log. And if I start taking functional derivatives of the generating function with respect to these external sources, I can compute the stress tensor of the theory, the currents dual to this U1, and the verb of this operator O psi. Okay? Now, if this partition function, if this generating function is also, or if the theory is invariant under local gauge transformations of the external gauge field and the external sources, then you can write down something that looks like the conservation of the current, which is exactly the conservation of the current if I don't have external sources that break the U1, right? So that's conservation of electric current. And I will also have what is usually called the conservation of the stress tensor. Okay, so these are two equations that will exist universally in my theories. Great. So now I told you that I want to study things which are very close to some kind of thermal equilibrium, right? So I have these two equations, okay, this and that, and I want to see how much information I can extract out of it. In general, there is not much information that you can extract out of it. It's not a closed system of equations, right? But let me think about thermodynamic equilibrium, right? So thermodynamic equilibrium will be characterized by a fixed temperature T, a fixed chemical potential mu, and some kind of time-like killing vector, which exists in my theory, and it is telling me what the rest frame of the system is. These are all fixed things, okay? I'm fixing them. Now, if you let me fix those three quantities, and they are fixed, then the stress tensor and the current of the theory takes universally this form here. That's the ideal part of the fluid. Okay, based on very general arguments, this is the only form it can take. Now, what thermodynamics fixes is basically telling you that these functions are not independent, right? So there is some kind of free energy, which is also related to the pressure of the system. And if I start taking derivatives of this free energy with respect to temperature and chemical potential, I can compute the entropy and the charge density. And there is also this constraint. Okay? The energy plus pressure is chemical potential times charge density plus temperature times entropy. Okay, so that's thermal equilibrium. Now, if I start thinking about configurations which are very close to thermal equilibrium, well, you can say, by continuity, well, I cannot be too far away from this. I will start thinking of T, the fluid velocity V mu, and the chemical potential as having some weak dependence on space-time. And then I'm expecting that these expressions, the constitutive relations for the stress tensor and the current, will start receiving corrections which are proportional to now space-time derivatives of these quantities. Okay? So you can think of this part as an expansion in terms of derivatives of temperature, the fluid velocity, and the chemical potential that come with some coefficients. Okay? And these coefficients will be called the transport coefficients. In general, you don't know what they are. If you could do a microscopic calculation and take the limit, the hydrodynamic limit, you should be able to extract them. Okay? But it's not always possible. That would be a very hard job that you would have to do in general. So in total, now I have how many variables? So this is normalized to -1, right? Always. So it will have d components in a d plus 1 dimensional spacetime. It would have d independent components. I have temperature and the chemical potential. So now these equations form a closed system which I can actually solve, right? And I can do things with it. I can extract information. So that's the whole point of how hydrodynamics said in 5 minutes. Okay, so that's a normal fluid. Okay, that's the normal phase. There is no symmetry breaking yet. Now, what happens when I have a superfluid? When you have a superfluid, you basically have this condensate. Well, it's basically, you know, this operator, complex operator, and the VEV is a complex number, so it has a phase. And that phase can be anything. The free energy or the energetically doesn't take anything to move this phase around, okay? So that phase now becomes part of the story. It's another light degree of freedom, and you can almost take as a definition of a superfluid that you have to include just a massless phase in your theory. Now, the way that this phase will enter the previous discussion is through a one form, which has to be gauge invariant. Okay? So I have to form a gauge invariant quantity. This is a one form or a vector, whatever you like. And I have to somehow include it in the theory. Now, the ideal part of the stress tensor in thermal equilibrium will take an additional term, right, as compared to this expression. And there will also be an additional term in the electric current. That additional term in the electric current is the supercurrent. You can basically have a current in your system, even though it might not be moving at all, right? You are in the rest frame, but you can have a supercurrent which doesn't dissipate at all, never. And for those that have heard about superfluids before, you see this combination that appears here in the stress tensor and in the electric current, if you form the combination that computes for you the heat current, the superfluid velocity or psi will drop out, which is telling you that, you know, superfluids are about transporting electric current, but not heat. Okay? Good. So psi, this one form psi, will also appear in thermodynamics. So your free energy is also going to depend on the norm of psi. And a new quantity, a new susceptibility, chi jj, which is the current susceptibility, will show up as a thermodynamic quantity. Now, I have written one more equation which relates the chemical potential and the superfluid velocity, and this is just fixed by gauge invariance, right? So from the thermodynamics point of view, what you would call the chemical potential would be AT. But AT is not gauge invariant. So I have to form this combination of d theta with AT, form a gauge invariant combination, and that gives me an additional equation for my system of, in my system of equations, right? So I have introduced another scalar theta, which is dynamical, but at the same time I introduced one more equation. So that's again a closed system of equations. Okay? Now, a naive question that you can ask is, how do I go from this to that? Well, as I'm approaching the critical point, this current susceptibility actually goes to 0. Okay, so immediately you see that the ideal part of the stress tensor becomes exactly what I would expect for a normal fluid. However, what happens with this part, the corrections, the dissipative corrections, is quite dramatic. So we had a couple of papers with Christiana and Polidoros, maybe a couple of years ago, where we actually computed the transport coefficients for holographic theories. And what you can see is that as you approach the critical point, this series just breaks down. Okay, the transport coefficients blow up. So it's not like these dissipative parts will just have a smooth limit where they will just go here. There is something dramatic that happens. And this is what I want to study. What happens really at this transition? Okay, in general, that would be a complicated question, but you can focus now on a relevant sector of this hydrodynamics theory. So I will basically just freeze the stress tensor for the time being. And how am I going to do this? I'm just going to fix the temperature and I'm going to fix the fluid velocity to just be the time-like killing vector in the theory. So I'm basically ignoring the normal fluid. Okay? So in this limit, with Polydorus, we are studying the more general problem, but I think I want to make my life easier and discuss. Yes? No, but people did that in the past. I mean, you can think of just a sector.
No, but what I'm saying is, can you have a situation in which this happens?
Neutral superfluids. They don't couple to the stress tensor at all. No, you have to have background charge. Well, at the non-linear level, yes, they will couple, but I'm mostly interested in the perturbative question. Okay, it's already relevant there. I mean, what happens with the transport coefficients? They show up even at the linearized level. Okay, so then I will just focus on the sector that has to do with charge density. For the normal fluid, this is just the chemical potential, right? There's not much. So if I perturb the constitutive relation I had before, from the time component, I will find the charge susceptibility times the variation of the chemical potential. And from the spatial components of the current, I will write for you the first dissipative part, okay? So when you are away from thermal equilibrium, delta mu would be homogeneous everywhere. A current will show up that will want to bring your system back to thermal equilibrium. So it will want to basically, transfer charge so that mu will become homogeneous again. So the current will be proportional to some derivative of the chemical potential, of the local chemical potential. And lambda nu is one of these numbers that I talked to you about, the transport coefficients. Good. Now, when I consider superfluids, I will have the ideal part of the superfluid, that's the supercurrent that I wrote before. I will still have this first dissipative correction, and in the time component, I will have to allow for dissipative corrections as well. Here it has to do with counting of time derivatives and how small they can be. So in the normal phase, basically time derivative is not allowed because time derivatives are much smaller. But in the superfluid phase, I have to allow for another term. Okay? Well, you see, because there is no ideal part in the current for the normal phase, if I look at the conservation of the current, time derivatives will be like squares of the spatial derivatives. Right? So a time derivative of this would have to be matched with a spatial derivative of that.
Second time derivatives will be fourth order. I wonder about this term.
Which one? Here?
The one down. The second derivative of mu, of delta mu. Here.
Over here. Okay, so in this case, you see the time derivative and the spatial derivative will be of the same order because of the current susceptibility. Okay? So you made me count. Thanks. Okay, so now I can do perturbations and see basically what the normal modes or the quasi-normal modes of this system will be. So in the normal phase, all I will have is a dispersion relation between omega and k. It will be diffusive. And in the superfluid phase, I will have a wave, basically. Okay, so it will have a linear part in k and a quadratic part in k. And crucially, I find two modes here, not one. Okay? Now, what I was talking to you about before, so I want you to focus on this part. So you might wonder, how does this turn into that as I approach the transition, and it doesn't, okay? So chi_jj goes to 0, but as we have shown with Polydorus, zeta 3 blows up, actually. So this expansion breaks down very quickly. It's a transport coefficient. It's called the third bulk viscosity. So zeta 3 blows up, but the product of chi_jj and zeta 3 stays finite. So if you were just looking at quasi-normal modes, you would never notice that the hydrodynamic expansion basically breaks down. This quasi-normal mode just remains nice, even up to the transition. Nothing happens to it. Sorry? I will tell you now. Okay, so, but to understand what's going on and probably come closer to Kostas's question, let me look at all the modes in the theory, and including the ones that I have thrown away by looking at just the effective theory. So as I'm approaching the transition from above, from the normal phase, what I have is the diffusive mode, which is described in hydrodynamics, right? So that's this mode. And I also have a couple of modes which approach the origin from the charged scalar operator, okay? So from the point of view of the superfluid, I have my second sound modes. These are basically two modes, the two modes. They are described in the effective theory, but I also have an amplitude mode. That's the mode that has to do with the amplitude of the condensate, which becomes very light. So what I have done basically is, in both cases, I have integrated out something which becomes gapless, close to the transition. And this is why these transport coefficients just blow up. So what we want now is to construct basically a bigger theory, which will include this charged operator, okay, this charged scalar. And since you have a question?
Yeah, well, okay, finish your...
Okay. So, and since I'm introducing now basically the amplitude, which together with the phase will form a complex scalar, I have to tell you what this equation is, okay? Yes?
This is taking into account the fluctuations, integrating out fluctuations, right? I mean, do you get anomalous dimensions in all of these?
Ah, what a nice question. Look, this is all coming from holography, so it's mean field theory. It's a large n limit.
Okay, that's what, okay, it is still mean field theory.
Yes, it is mean field theory. Yes, there is a very valid question of how these things are going to behave when I start taking thermal fluctuations into account, and I do RG flows, I do all these things, yes. Okay, so I somehow have to tell you what this equation for this psi is, okay? That will give me now a closed system. I think I'm getting closer to your question. So let me think about thermodynamics before jumping to the dynamics. So what I would do very close to the transition is basically you could come up, you could integrate out, heavy modes, all the UV stuff, and you would probably be able to come up with an order parameter which you basically don't integrate, okay, in the partition function. And that would give you the Ginzburg-Landau free energy, W naught. And then you integrate over this over this order parameter psi and psi star, and you would find the free energy of the system, okay? Now, what you might be tempted to do is to take a saddle point approximation or a semi-classical approximation. Basically, throw away all the thermal fluctuations of psi. Now, why is coming up with Ginzburg-Landau free energy useful? Well, it is useful because you can assume certain analyticity properties for psi. You can assume that W naught is analytic in psi. It has like a polynomial expansion, right? There is nothing non-analytic. So if you do the saddle point approximation, the semi-classical approximation, basically you find that when this coefficient alpha prime changes sign with temperature, you do get a finite condensate. You minimize this free energy, and you find that the minimum actually has a non-zero psi. Okay, so that could give you a second-order transition.
Sorry, this is not always true, right? If you have non-trivial strongly coupled theories, this effective action is not analytic. Dimensions, for example, are not integers, or
That's not the effective action. I have not, okay, to find the effective action, I would have to integrate over psi, introduce j's, the sources, and then trade the j's for the vevs of psi. That would be the effective action. No, that's not the effective action.
So that's the source action.
Yeah.
Yet that can be another.
So I have not integrated basically over the fields, right?
What is W0 then? If you haven't integrated over the field?
Well,
It's the effective action.
you can imagine that you have integrated out all the massive degrees of freedom, right?
So that's the Wilsonian action.
Yes.
But this is still massive. It has a quadratic term,
Yes, so it becomes much less at the critical point.
And there's no time derivative?
No, that's just thermodynamics. Okay, good. But now we are coming closer to your question. But so you would have your semi-classical approximation, and you would still want to integrate over fluctuations, right? So that would change the answer for the free energy, and you would find an additional term from the fluctuations, which actually diverges even stronger than the free energy, if you are in dimensions smaller than 4, or if you are at finite n. Okay, so at infinite n, I can just forget about this term, and that brings us to holography. Okay, sorry. N can be the number of copies of the field, or the number of degrees of freedom. You can have an additional index, right? You can. Okay. Good. Now, I was talking about the complex field. Let's take the much simpler case of just a scalar field, which in the language of Hohenberg and Halperin, that would be model A. Okay, there is no U1 in this case. There is just a scalar field which takes some kind of vev, and I want to come up with the equation of motion for it close to criticality. Okay. So one of the natural things you can write down is on the left-hand side just the time derivative. Okay, there is dynamics. I want to find the time evolution of phi. On the right-hand side, I should have things which are basically 0 at thermal equilibrium. Okay? So at thermal equilibrium, by definition, the derivative of the free energy with respect to the value of the field phi is equal to the external sources, right? That's the definition of the external sources, basically. So that's 0 at equilibrium. When I'm a little bit away from equilibrium, I can say that the time derivative of phi is basically proportional by how much offset this is from its ground state. So I'm introducing an additional number gamma naught, which is basically representing damping, and we agreed that thermal fluctuations are important at finite n, so we'll have some kind of thermal noise on the right-hand side. So that's basically the Langevin equation. And the thermal noise, will just be Gaussian noise, and its strength will be characterized by a number d. So I have introduced two numbers here, gamma naught, the kinetic coefficient, which is a transport coefficient, and an additional number d, which has to do with thermal fluctuations. Now, you might say, okay, are these two numbers independent? Well, no, they are not independent. You can write down, since this is a stochastic system, you can write down a Fokker-Planck equation for the time evolution of the probability distribution of all these configurations. And if you are a physicist, you will say, okay, I want this current in probability space to be equal to 0 whenever my distribution is equal to the Boltzmann distribution, okay? And in the way that these parameters d and gamma naught enter in this probability current, you will find, you will get the Boltzmann distribution as long as this d and this gamma naught are related to each other. And this is a kind of an Einstein relation. Okay, so this is one way to think about the dynamics. It's not obvious that this is the only thing that you can write down. Even in this simple case that you just have a scalar, you could have, higher time derivatives. Why not? It's not obvious at all why a single derivative would even work at the limit that we are working here. Now, if I consider a complex phase, a complex field, I will have to write down something more complicated. This part is exactly what I wrote for the scalar field. I have to introduce an additional term, which is basically the Josephson relation. So the derivative of this this potential with respect to rho, of this free energy with respect to rho, is the chemical potential. And if you just look at this equation, this is just a Josephson relation that I wrote down before, and mu was just the derivative of the phase of the field psi. Now, it might not be obvious at all, but this is the conservation of the current that you get from this U1. So this is just a grad mu J mu equation written in a very old fashion. And I still need to introduce, thermal fields, thermal noise fluctuations that come in theta and zeta. So the question is, what is this gamma naught, and whether this actually describes any system, okay? Any system that we can compute exactly. And here this slide is just a small explanation of how this equation basically boils down to the conservation of the current, right? So I can probably just go through that quickly. So what is the plan? The plan is to now go, that is just classical, right? There is no thermal fluctuation. So whenever I'm looking at a large N theory, which has such a transition, I should be able to check that this is actually true, this part of the equation. And that part of the equation, which is thermal noise, I can always come back to it later. I can add it by hand. Or I can even understand this system of equations in the Keldy-Schwinger formalism. And it just comes from a very consistent formalism of the theory at finite temperature. I can just go back and do all my computations in Keldy-Schwinger. Yes?
So what is inside the red line is classical hydrodynamics just obtained from some effective action.
That's correct. And on the right-hand side, it's stuff that I can throw away at large N. So it's just classical dynamics in the end. Okay, so let me look at the problem from the holographic point of view. So in holography, the ground state is represented by ADS space, and it is very useful to think of it as a foliation with the leaves being just Minkowski space. You very quickly see the invariance under Lorentz transformations just from this part of the metric. And you can also see very quickly scale invariance, just scale R by 1 over lambda, T and X by lambda, and you will very quickly see that this is scale invariant. There is also the special conformal transformations of a CFT. These are a bit harder to see. But this is basically the ground state of any holographic theory of a CFT in holography. Now, the model that I want to consider in holography that will basically describe what I was talking to you about from the field theory point of view is what is called the probe limit, right? So there will be no dynamics for the metric. The metric will be frozen to some fixed background. I will definitely need to have a complex scalar psi. There is a Maxwell field in the bulk which is dual to the electric current on the boundary, and the charged field is charged under gauge transformations of the Maxwell field. And I'm also introducing a scalar phi because conformal invariance is too restrictive sometimes. Okay, I will use the scalar phi to introduce another scale in the system and break conformal invariance. Okay, so what do I do? What do I want to do from the holographic point of view? Well, as I'm approaching the boundary of ADS at R goes to infinity, I want to slightly deform the metric, the boundary metric. This is like coupling the dual theory to a curved background. Asymptotically, the gauge fields in the bulk asymptote to the sources of the electric current in the boundary theory, and I can also introduce scalar sources phi s. Then what do I want to do? So I want to solve the equations of motion, make sure that everything is regular, and then the bulk action, or the gravitational action, will be a functional of phi s, a mu, of the sources of the scalars, of the sources of the gauge field, and the external metric, the boundary metric delta G mu nu. And then if I imagine that if I take the semi-classical approximation, then the on-shell action will give me precisely the partition function. And if I take functional derivatives with respect to boundary sources, I will compute the waves of the theory. So how does it look like? I have this slide so that I can introduce some notation. Right, so what I want to have is the conformal boundary at infinity, and somewhere in the bulk, I will have a horizon, okay? And the temperature of that horizon will be equal to the temperature of the dual theory. Moreover, the scalar psi, as far as the thermal states go, will take some constant value on this horizon, okay, which I call psi h. From the gauge field, I can introduce fluxes, both through the horizon as well as through the boundary. And the flux at the boundary, which I call rho, will be the charge of the dual theory, the conserved charge of the dual theory. Now, I can also introduce the flux through the horizon, which I call rho h. And as long as I don't have any symmetry breaking, you know, A mu will be satisfying Maxwell's equations in the bulk. So through Gauss's theorem, rho h will be equal to rho. But as soon as I break the U1 symmetry, I don't satisfy Maxwell's equations anymore. Rho h will be different from rho. And you can always ask, okay, then why is rho h important? It would be meaningless. Well, I will tell you that rho h actually enters in the discussion at some point through the transport coefficients. Right? So this is how things look like. You see AT asymptotes to mu, the chemical potential. I don't want to have any source for the complex scalar psi because I want it to take a wave spontaneously. I'm solving the background equations if I find some black hole solution. Okay, so after you do that, you want to study fluctuations, right? So because you want to do hydrodynamics, you want to extract the effective theory of dynamics, you have to understand how these bulk fields behave. Now, after you claim victory and solving the equations, what do you want to do? As I told you, you want to take the bulk action. You know, the action will be written in terms of some Lagrangian density, which will be function of first derivatives of fields. Phi can be any field, the metric, the gauge field, anything. And phi itself, you would vary the action with respect to this field. And at the end of the day, you would have to compute this quantity at the boundary. Okay, and that could give you the waves. Now, it is always useful to think of this quantity as a momentum, right? So Yannis has told us that this is a very good thing to do, and you can actually do a lot of things with it. Now, so this is where all the money is. Okay, so if I solve the equations, this is what I'm interested in ultimately. So I can extract these things by thinking a bit differently. Instead of actually solving equations, I can think of the symplectic current, of the gravitational symplectic current that I can form. And by construction, as long as I'm doing perturbations, the divergence of the symplectic current will be zero, identically, trivially, because of the equations of motion. Okay? So to form the symplectic current, I basically need two perturbative solutions. So as I will try to argue, if you are clever enough and you choose these solutions wisely, you can extract non-trivial information. So what I take for granted is the perturbations that I can form just by varying thermodynamic quantities. The temperature of the backgrounds, the chemical potentials, these are all given somehow. And the hydrodynamic modes I want to construct are basically deformations of these thermodynamic variations, right? So I take a thermodynamic variation, I dress it a little bit with some space-time dependence, and I have to correct this perturbation. And the first correction will basically give me the first dissipative correction, and this is what I am after when I'm doing hydrodynamics. So instead of actually solving the bulk equations, I can construct the symplectic current by using this perturbation and that perturbation, and I can extract information from the boundary. So, and this is how the radial component of the symplectic current looks like when you evaluate it asymptotically. So you can see, so that's the VEV basically of the dual operator, that's the current, and that's the stress tensor. So if I choose wisely, I can extract information from it. So this is the kind of game that we played with Polydoros, and we've extracted the dynamics of this field psi, and actually, almost to our surprise, it was exactly the model F of Hohenberg and Halperin. That's exactly the same classical dynamics that you satisfy. So this free energy basically is parameterized by some thermodynamic quantities. Yes, I mean, when you do holography, these are fixed by the background black holes, but these are nothing but thermodynamics. So the interesting stuff comes basically from the transport coefficient gamma naught and this transport coefficient lambda naught. Okay, so that could be something that you would have to do an honest microscopic calculation in order to extract from a theory. And how is this fixed? So lambda naught is basically just the value of this gauge coupling evaluated at the horizon. Okay, you take your background black hole, you see how this gauge coupling looks at exactly the horizon, and lambda naught is exactly that. Now gamma naught, the kinetic coefficient that I introduced for you today, can be written in terms of, that's the entropy density. That is the value of the complex scalar field on the horizon at thermal equilibrium. And there is also a complex part, which is the difference between the charge density at infinity and the charge density on the horizon. Okay, so that difference is basically fixing the complex part, the imaginary part of gamma naught, of this kinetic coefficient. And you can actually see the details of why these superfluid coefficients blow up. You know, you can integrate out the amplitude, and you can actually come up with a third bulk viscosity, and it will be, of course, blowing up. What else do I want to tell you? Right. So if I still look at this theory, you know, this effective theory, basically you have, in the normal phase, these three modes, the complex scalar, the diffusion mode. If I look at very small momenta right below the critical temperature, I will have my two diffusion modes and the gapped Higgs mode. Okay, that will be the amplitude mode, which is basically gapped, and it has a very specific value of the gap. And I want to talk to you now about the crossover. So if I start from small values of k and I start increasing them, then there will be a critical value of k where the behavior will completely change, and at very large values of k, I will end up with a normal phase degrees of freedom. So if I look at neutral superfluids, for example, for very small values of k, I have those two sound modes and the gapped mode. As I'm increasing the value of k, the two sound modes start approaching the imaginary axis, they collide, and as I take k even larger, then one of the two sound modes basically turns into one of the two modes that I would expect from the complex scalar. And the other one remains diffusive. So this is, if you don't believe me that this is the right theory to describe these quasi-normal modes, we have done with Polydorus numerics. So the dots are actual quasi-normal modes that you find from the black hole solutions. You perturb it. Mathematica will find some kind of solution. It will give you the quasi-normal modes, and you put a dot. So the blue lines are actually plots of the analytic expressions. So this is, I believe, the real part over k of the dispersion relation for the sound mode. You see for small values of k that does indeed go linearly. As I'm increasing the value of k, this is kc, the critical value. They collide on the real axis, and after that, they both acquire an imaginary part. So this is the imaginary part over k squared. Okay, so at large values of k, this is basically telling you that the imaginary part is becoming quadratic. Right, so I think I finished. Right, so in this probe limit of holography, yes, these black holes are captured by the model F of Hohenberg and Halperin. The question is, what happens when I bring the stress tensor into account and the normal fluid? Yes, there was a relevant question about what happens when I take into account thermal fluctuations. For that, we would have to do much harder field theory computations. Holography wouldn't have too much to tell us in its classical limit, at least. And of course, the question, after you come up with this more general theory that includes the fluid velocity, normal fluid velocity, is what happens with the fixed points, whether there is any new fixed points. So, thank you. Yes.
It was a very interesting talk, Aristo. Perhaps it's elementary, I was lost, but it's, I think, fascinating that you find the holographic distribution properties or coefficients. Perhaps this is for future work, but I was just trying to understand
Well,
if you have some predictive or something
okay.
that field theory on its own would not be able to provide.
For example, when people wrote down these theories, it was not entirely clear what was happening with this gamma naught. Was it finite? Was it going to zero? That's one question. The other is, if you ask me today, this is not the most general thing you can write. The fact that you have, for example, no second derivatives in that equation is non-trivial. So what holography has to say, so today we just confirmed that you can basically understand things from some Ginzburg-Landau potential in the classical limit. So what holography will have to say is when you include the stress tensor and the normal fluid velocity. That has not been done.
Thanks a lot.
Yes.
First of all, I guess your phase transition is second order, right?
That's correct.
Okay. In holography, you can have transitions which are not second order, they can be higher order. Can you imagine what would be the difference in that situation? There are even DKT transitions at the moment.
We would have to be very careful about the expansion that we are doing in that case. So the bookkeeping would be different. So it's not automatic to me right now. I haven't thought about it carefully, but yeah, there will be differences.
The Langevin also, in relation to the previous question that you wrote, of course, higher order terms, in particular gamma zero, it's a long time limit of correlating, and it has corrections which are irrelevant, of course, when you go to the infrared. Is that a correlator you can compute in the programming theory?
You mean
That's
some?
a kind of force-force correlation.
You can only capture the tail, right? So not the subleading corrections that would come from the noise.
But the noise.
No, wait. So yes, we are critical. No, the noise would be crucial. So I don't. You would just find the mean field theory result from holography.
That's because you have a mean field theory position. If the position was not mean field theory, you would not get.
You mean find something non-mean field theory from holography?
Yeah. No, people have found non-mean field theory from holography if the transitions are different.
All right, but that could require some kind of non-analytic potential or something like that, right?
Indeed, you're actually doing non-analytic, and
Even in model F, if you're close to, if you include fluctuations, you do get an analytic.
But that's different, right?
What I'm saying is having order parameters that have non-trivial dimensions,
I think that
non-integers.
I think the analog would be take a Ginzburg-Landau potential, which has psi to the 3/2.
Yeah, but what I'm saying is even with the 5F and A models, if you're close, if you do 4 minus
No, if
epsilon,
you
yeah, you
integrate
will
Yeah,
out
get
yeah,
the
yeah.
non-analyticity. Yeah.
But
dimensions.
Exactly. Yeah.
but this is purely thermal fluctuations, right? I think Elias is asking about
About
Already,
mean field
it's
theory.
non-trivial, it's non-mean field.
Okay.
Already the action is not analytic.
True.
Yeah. Yanni.
So, do you have any field theory understanding of why holography gives you the model F?
Any field theory understanding of why?
Well, can you anticipate? I mean, that you will get model F.
In the way that I described it, yes, it's something very natural to write down. You can go through the details and you can see that there is almost no way out of it. All right. So if you say I want to have the Josephson relation, but then that should not change the dissipation properties of the system, almost everything is fixed in these equations. There is a little bit of freedom, but not too much.
Perhaps we can move on to the next.
Yeah. Thank you.
Thank you very much.
Control L.
very happy to have Ilias Kiritsis talking to us about confining holographic QFTs on ADS.
Thank you. First of all, to say that I'm very happy to see that this meeting is going on now for many years. It's a very good idea because it brings the community, the Greek community of quantum field theory and string theory together, and I hope it will go on also in the future. And I'd like to thank also the organizers for giving me the forum to present my work. So what I would like to describe today is some work we've been doing on the general topic of theories on ADS, as I will try to argue, and as some of you know, this is a topic that has many facets. In fact, it unites several types of problems. The first type of problem is the issue of holographic interfaces between two different quantum field theories and the notion of holographic defects. Of course, this is a concept that goes beyond holography. It's a concept in quantum field theory. Another topic which is related is the notion of proximity in quantum field theory. The third topic is the dynamics of quantum field theories defined on a fixed ADS space, and a related concept is that of Euclidean wormholes. And I'll try to at least indicate why all of these things are related. So let me first start with the notion of quantum field theory on ADS space. This is a problem that was first seriously addressed by Cullen and Wilczek in the early 90s. Their interest was infrared physics, in particular the infrared physics of gauge theories, and in fact their motivation had to do with the infrared divergences that QCD perturbation theory has once you start doing calculations. The important property, in fact, of ADS space for that purpose was that even massless fields had propagators which vanished exponentially at large distances, like massive fields do in flat space. Of course, you could be on the sphere, but on the sphere you don't have a large distance limit. ADS has infinite volume. This property, in fact, is related to the fact that the Laplacian and other relevant operators have a gap when you are on ADS. So in general, this property of ADS essentially quenches strong infrared physics, and this is typically a problem in several quantum field theories. There is an extra ingredient, in fact, which is that when you consider quantum field theory and ADS, this theory must realize the ADS symmetry, and this ADS symmetry is like conformal invariance in one less dimension. That's something also that appeared in Kostas Kendaris' talk earlier. Also, the structure of instantons is expected to be different on ADS. In fact, in flat space and in QCD, we expect to have an instanton liquid rather than a dilute instanton gas, as it's known since a long time. And moreover, if you go above the deconfinement phase transition, in that case, the instanton liquid turns into an instanton gas. However, as Cullen and Wilczek argued, in ADS, you expect generically an instanton gas at all scales. Another issue is that if you are in ADS, chiral invariance for Fermius is broken by boundary conditions, and this brings in an important ingredient one would have to remember when one considers quantum field theory and ADS. You need boundary conditions. So let's describe, for example, what a confining asymptotically free theory like Young-Mills, for example, would be expected to look like on ADS4. In that case, you have two types of boundary conditions: electric, which are Dirichlet boundary conditions, and magnetic, which are Neumann. This is something that has been discussed earlier in the past by Harony and company. If you have electric boundary conditions, then gluons are allowed in ADS. They are gapped, and there is an SUN global symmetry at weak coupling. This is a global symmetry that appears on the boundary, and therefore you have only boundary currents. If, on the other hand, you have magnetic boundary conditions, then electric charges are not allowed in the back. Therefore, you have apparent O order 1 degrees of freedom if you have SUN. And in this case, there is kinematical confinement that's imposed, in fact, by the boundary conditions. And in particular, as these people argued, if you have a typical asymptotically free gauge theory with Dirichlet boundary conditions, like standard Young-Mills, you expect a kind of a transition that you can call it a confinement phase transition, because if I call L the ADS radius, the curvature is 1 over L square, then, and lambda is the characteristic scale, let's say, of Young-Mills. If this dimensionless combination is much bigger than 1, then you are in a confining phase, and this is the phase, of course, that asymptotes to the theory on flat space. But generically, you would expect that if lambda L is much smaller than 1, then you are in a different phase, which people call this the deconfined phase. Now, if on the other hand you have magnetic boundary conditions, then as I said, you expect kinematical confinement at all scales, a free energy of order 1. And in this kind of case, as I said, no electric charges are allowed in the bulk, and you don't expect, in this case, a phase transition. Now, typically we use Wilson loops to track whether you have confinement or not, but this is tricky in ADS. And the reason is that in ADS, area and perimeter scale the same way once you get large distances. And up to today, there is no clear, detailed understanding how you can use a Wilson loop to tell whether you have confinement or not. There may be, in fact, some leading difference that may tell the difference, but that's not known. If you are on ADS with Poincaré coordinates, in fact, in that case, you have two classes of Wilson loops, and these may have different behavior for length and area, but this is something that hasn't been computed so far. On the other hand, also, it's important to remember that if you consider a quantum field theory on a manifold in two different coordinate systems, this is a different quantum field theory in general. It's not the same.
Boundary conditions, right? Not the coordinates.
No, the coordinates also play a role.
If you have conservation of energy, then you have different Fisman values.
Yes, but differential variance is not a symmetry of quantum field theory because it's broken by the vacuum. As you know very well, if you consider free quantum field theory on mini-universe or in flat space, this is not the same. That's what I mean. The vacuum quantization breaks differential variance in a theory in a fixed background.
You still have conservation of energy.
Conservation of energy has nothing to do with that. Let's discuss it afterwards. I mean, the example I gave you answers your worry. Let me describe the notion of interfaces. You have, let's say, R4. You take a three-dimensional hyperplane. It splits R4 in two parts. You put a CFT on one part. You can put the same or another CFT in the other part, and then you have a wall between the two. And then you can put a theory even on this defect. That's general form of an interface. If you are in flat space, in fact, you can map this into two ADS spaces by doing a conformal transformation on the flat metric in this way. Y, let's say, is the direction transverse to the interface. And then one can conformally map this situation, in fact, to two ADS spaces in Poincaré coordinates, which are touching along their common boundary. And in fact, this makes contact with solutions that have been found in holography. If the interface is conformal, then just because of this, the interface has codimension 1. You expect an OD, 1 symmetry. And this is precisely the symmetry that's realized in these coordinates, and that's why this coordinate system is useful. Now, if you want to build a holographic picture for something like this, then let's say the bulk, the gravitational bulk, is d plus 1 dimensional. Then what you would need to realize this symmetry is to have a metric, which is a conical type of metric with slices, which are ADS D metrics. So zeta mu, let's say, is a unit radius ADS metric, and then you have a scale factor, and U is the holographic coordinate. As you move the holographic coordinate, you still have the same slice, but the size changes. Now, here you would have an asymptotically ADS boundary, let's say, as U goes to -infinity, and in this case, you can put your boundary conditions, and with these types of metrics, the boundary conditions specify that the metric on which you define your theory, your holographic theory, is an ADS-D metric. So these types of solutions capture, in fact, states in this theory which have this symmetry. Now, if it happens that the full holographic theory is scale invariant, then the symmetry is enhanced to O1, D plus 1. And in this case, of course, the total solution is the space that realizes its full symmetry, which is ADS D plus 1. And in this parameterization, where the slices are ADS D, then the scale factor becomes cosh of U over L. And as you can already note, unlike the cases we usually describe in ADS CFT, this is a case where the scale factor is not monotonic. So in this case, this scale factor has two apparent ADS boundaries, one which I call B plus, which is at U equals minus infinity, and the other that I will call B minus is at U plus infinity. The metric is locally ADS, and in fact, it can be mapped to global ADS by large diffeomorphisms. And in the Euclidean case, these two boundaries are isomorphic to half balls, and they intersect at the equator. So it's a picture like this. This is one boundary, this is the other, and this is their intersection. And this intersection corresponds to a defect in the dual quantum field theory. So in the bulk ADS case, indeed, the solution would be interpreted as a CFT on ADS-D, or up to by doing a conformal transformation as two copies of the same CFT that are interacting through a common boundary, as I showed you in the picture with the interface. So in general, of course, this can become complicated. The solution need not to be ADS, but it can have these two pieces of the boundary. And in general, you can have different theories on the two sides of the interface. Now, if you use Poincare coordinates for the slices, then you get back to the picture where you have the CFTs on flat space sharing hyperplane in between. Now, let me try to describe another issue, which is wormholes and how it's related to the picture of interfaces I built here. And the difference, in fact, is the geometry of the slice. In all cases, the ansatz, the holographic ansatz, is this. This is a constant negative curvature manifold. So far, I took it to be ADS-D. But in general, it can be a different type of manifold. ADS-D has a boundary and infinite volume. But there are constant curvature manifolds that have finite volume, in particular a non-boundary. And in this case, the interpretation is different. So let me show you two pictures. This is the case, what the solution would look like if the slices, the constant curvature slices, are compact, for example, constant negative curvature manifolds. Examples are genus higher than 2 Riemann surfaces in 2 dimensions, or what is known as Schottky manifolds in higher dimensions. And in this case, the slice has finite volume, and this looks indeed like a wormhole. It has 2 boundaries, and then slices which have finite volume. If, on the other hand, it's a manifold which has infinite volume, then in this case, the 2 boundaries are connected via the common boundary, and this is the picture that you have in the interface. So therefore, these solutions, depending on what you consider as a constant curvature slice, have 2 different interpretations and different physics. Let me describe another concept that's due to Van Ramstok, and this is the notion of proximity in quantum field theory. The question, of course, has been posed a long time ago, and there are various ways of putting this question, but one possible way you can ask it is, if you have 2 quantum field theories, can they live in the same Hilbert space? In fact, there is a possible answer to this question, which looks natural, and the answer is that if there is a flow connecting, for example, 2 CFTs, then these necessarily live in the same Hilbert space. But Van Ramstok gave a different definition of proximity, and this definition would be, can you have 2 theories, which could be CFTs or QFTs, which can be separated by an interface? And if you can, then these can be called proximate, otherwise they cannot. And the question is, how do you define this notion of proximity by looking precisely at such interfaces? And I will have something to say later on. Already in holography, we know that this type of defect in a holographic context may be generated by bulk brane. That was what Takayaragi has argued. Or it may be represented by this large class of Janus-like solutions that many people have studied over the years. There is another problem, in fact, that is interesting with quantum field theories on ADS, and this has also contact point with what Kostas told us a couple of days ago, and this is that the S matrix of a quantum field theory on ADS is mapping to correlators of generically non-local CFT in one less dimension, non-local because this does not have a stress tensor. And in that case, in fact, the bulk crossing symmetry of S matrix elements maps to boundary bootstrap constraints. Kostas, in fact, realized it in the context of the usual ADS CFT, but the idea is similar. However, this is not something I will describe here. Already we heard quite a bit of it, about it from Kostas. So let me now focus in a set of theories in which I will do the studies of these types of problems. I'm simplifying by taking a single scalar in my theory, ignoring the other scalars. Whatever I will tell you, on the other hand, are valid for theories with many scalars. So you have gravity plus a single scalar plus a potential. And the ansatz for the metric is a conifold metric, which is sliced by negative constant curvature slices, and the scalar is a function of the radial coordinate, which is the holographic coordinate. And these types of solutions, in fact, are interpreted as ground states in the associated theories I'm studying. Now, the slice manifold, which I call M zeta, is any constant negative curvature Einstein metric, because the equations, in fact, you derive from it doesn't matter which manifold you have. It only matters what kind of constant curvature you have, and that's it, and that's constant. Now, you have two functions basically to find these solutions, phi and a, and basically what we have done is we systematically studied the solutions to these equations for negative curvature, and in general you can show that all regular solutions have generically two boundaries that in these coordinates are at u equals plus or minus infinity. I call these boundaries b plus and b minus. Of course, these are boundaries that touch. Both boundaries are conformal to the manifold you put on the slice, and the endpoints are always finite maxima, which I will call phi plus minus, of the bulk potential. And each solution, which means each function a of phi, corresponds either to a wormhole solution if the manifold mz is compact, and in that case it connects two different CFTs, a CFT that's on one boundary to the CFT that's on the other boundary. And if it's non-compact, it's an interface solution, and the interface is between these two different CFTs.
So are you using particular bulk potential or like
Any potential.
well, it has to have some conditions, I guess, right?
Conditions for what?
Like asymptotically, how?
I haven't gone so far. It's finite solutions, because if you go asymptotically, as you know, you have singularities. So that's what I will come later on when I will discuss confining theories. For the moment, these are finite solutions. In what I will show you, I will have to define these two superpotentials. W is in fact a dot, and S is phi dot, because these are the things that you need to describe the types of solutions. And let me introduce also two concepts, what I call an A bounds. So that's a place where A dot equal to 0, which means W equal to 0, which means that it's a place where the scale factor turns around, and the other is a phi bounds, which is the same thing for the scalar, that is the scalar change direction. And with this, I can show you now what, in general, the solutions are. So you can pick a dimension. We picked d equal 4. You can pick a generic potential. It doesn't matter, because these are general properties. This is a potential, as you see, that has two maxima and a minimum. And the maxima correspond, as usual, to the UV part of CFTs, the minimum to an infrared part of a CFT. And in this case, all solutions are classified by two parameters. The first parameter is phi 0, is the position of the scalar for which you have the bounds, that is, the scale factor turns around. and the second is the phi dot at this place. So these are two real variables, and for each value for this, you have a single solution. That's what, in general, the solution would look like. So this is where this is phi, the scalar field. This is where one of the maximum of the potential is. That's where the other maximum of the potential is. The solutions have to end up at maxima. And in fact, what you get is, for example, either a solution that starts from one maximum, goes around, and ends back in the same maximum. And that would correspond to an interface where on the two sides you have the same CFT. Or, in general, you can have a solution that starts from here and crosses over to this other maximum, and that would be an interface where on the two sides you have two different CFTs. And of course, these solutions can do different things. Either they can go straight like this, or they can start going in that direction and then have a phi bounce and then turn around and go here. Or they can do even more complicated things I haven't seen, doing like this and going there. The same thing happens here. So there is a complicated set of solutions that can go back and forth, but eventually they end up at the two maxima, either the same maximum or a different maximum. So that's the general structure. Yeah.
Is there something like a C function? Welcome.
I'll come to the end, so keep your questions for the moment. So that's what, in fact, the space of solutions looks like in this phi 0 as 0 plane, which are the two real numbers that classify the solutions. So the orange regions here are regions in which you start from one maximum and you go to the other maximum without doing complicated things in between. However, if you come here, you start from the left maximum, you go to the right maximum, but you do one turn in phi space. And there are more complicated solutions we haven't shown, which are up here. Here, in the green part, this is a solution that starts from one maximum, goes around, and goes back to the same maximum with just one turn. But then you can do two turns, and it's this class of solutions. And as you understand, this type of figure becomes more and more complicated as you go out in the space where you have more and more complicated solutions. All of these solutions are regular.
This corresponds both to wormhole solutions and to...
You can construct from them either wormhole or interface solutions, depending whether your manifold that you put back is compact or not compact.
Every point corresponds
to both types of solutions, depending on what manifold, because the equations do not depend on what manifold you do, but only on its constant curvature. So this is what happens when you run, let's say, at finite places in the scalar field space. And now I'm coming to what Ioannis asked me before. What happens when you go to boundaries of field space? And that's where, in fact, you have to go if, in this context, with a single scalar, you want to construct a confining theory. In fact, it's well known that if you try to construct a confining theory with a single scalar, you have to run to the boundary of field space. And in this case, the solutions are singular, because you get naked singularities in such types of solutions. But this is a problem that has been studied in the past, first by Gupser, who, in fact, classified such singularities as acceptable and non-acceptable, or good and bad in that notion. And in fact, there is an intuition behind why some singularities can be acceptable. And the idea is that they could be resolvable either if you go to higher dimensions, as it happens with cigar geometries, or even by stringy effects. And there are criteria for that. So these are the types of solutions. So when we discuss now regular solutions, these would be regular Gupser. They're actually singular, but they satisfy certain conditions that make them holographically acceptable. So all of these solutions for flat slices, that is corresponding to theories which are on flat space, have been studied in the past. And indeed, as I will argue, some of them correspond to confining theories. So let me parameterize now the potential asymptotically. In this case, as we know from supergravity and string theory, the potentials asymptote as exponentials of canonically normalized fields. So that's how I will parameterize my potential, let's say, when phi goes to infinity, in terms of an exponent here that I called A. And in fact, it is known already from previous analysis, considering these theories in flat space, that if A is in that range, then the theory is non-confining. And if this theory is in between this number and this number, which is also known as the Gupser bound, this theory is confining. And if the exponent is bigger than the so-called Gupser bound, the singularity is too strong. So that would be the UV of your theory, and an asymptotic region where it behaves exponentially. And if you wish, if you find solutions like this, the interpretation would be a theory whose UV is this CFT, and then the infrared would be confining. And as usually happens in flat space, such theories are known to have a mass gap. So, and then I would consider, as I said, regular solutions, and regular here has quote marks, regular a la Gupser. So what one finds in such cases is three classes of regular solutions a la Gupser. There are two boundary solutions like before. That is theory that starts at the UV fixed point, at the maximum, goes around, goes back to the maximum. These are perfectly regular solutions. There is no singularity because they do not run off to infinity. And their interpretation is what we discussed already. They are interface or wormhole-like solutions. Then, in this case, unlike in the finite case, you find one-boundary solutions because these are solutions that start at the maximum and then they go down to minus infinity, but in a regular way. And these are dual to confining theories on ADS. And by confining here, I mean theories that confine in flat space. I don't know if they confine really in ADS. That has to be computed. And then finally, you have a third class of solutions which start at phi minus infinity and end at phi plus infinity, or they end back at phi minus infinity. These, of course, are regular on both sides, a la Gupser again, and we don't have an interpretation, although there are some ideas about such solutions. So let me show you the space of solutions in the same diagram as before. So these are the two parameters that classify the solutions. All the green part here are the regular solutions. They start at the maximum, they go back to the maximum, they correspond to interfaces. The blue solutions are the solutions that start at the maximum, they go off to infinity. The generic blue solutions here are singular, a la Gupser. However, if you look at these black lines, these are the subspace of solutions that are regular, a la Gupser. And finally, the red part are solutions that run off on both sides to infinity. And the generic such solution is singular. However, you see some yellow lines, and these yellow lines correspond to solutions that are regular on both sides. And in fact, the structure of the regular solutions is more complicated than what you can see on this diagram, because if you start blowing up the regions, for example, near the boundaries, you see that you have regular solutions here, you have regular solutions here, and if you blow this up even further, you see even more and more regular solutions. And as you will see later on, there is an infinite number of such lines as you approach the boundary. These are weird solutions that appear, in fact, at the boundary between these two. For example, suppose you approach here the end of the solutions that go from UV to UV, or you approach from here with these are solutions that go from UV to infinity. In that case, you get solutions that oscillate near the maximum more and more times as you approach. And in the end, when you approach the boundary, these solutions oscillate indefinitely. And these are oscillations both of the scalar field, but also of the scale factor, which is highly unusual.
Can you find this analytically, this area?
We do have an approximate, in fact, it's written, there is an approximate expression in terms of elliptic functions, in fact. And in fact, although we're using bottom-up potential, these solutions should exist in top-down situations, as I confirmed with Chris Rosen, who was looking at top-down situations. Now, what's the relation of these parameters that I use to classify the solution to the sources? That is, what kind of quantum field theories do these correspond to? And the only dimensionless number that the dual quantum field theory has, it has two scales. It has a characteristic scale, let's say lambda QCD, which is corresponding to a relevant coupling, and it has the curvature of ADS. Therefore, you can construct a dimensionless number that we call script R, or a dimensionless curvature, and that's the only parameter they have. So this is the physical, let's say, parameter of the dual quantum field theory, and this is a parameter that classifies the regular solutions in the infrared, and that's what it sort of looks like. That here, basically, green are solutions that go from the maximum to infinity, but they don't, the scale factor is monotonic. The blue are, all of these are regular solutions. The blue are solutions which go from the maximum to infinity, but the scale factor is non-monotonic, doing more and more ups and downs. And then finally, these are solutions that don't have a boundary. They go from plus infinity to minus infinity, and vice versa. As you can see, for every value of R, you have many. In fact, here, there's a pileup of an infinite number of saddle points. So you have an infinite number of possible solutions given a parameter or a coupling, if you wish, of your quantum field theory, unless the curvature, the dimensionless curvature, is very small, in which there is only a single saddle point. The other thing is that when you blow up the blue region, that's where you see what I told you before in words, that in fact you get an infinite number of saddle points in this case. And you note that both here and here, you have places where R goes to minus infinity. And what these correspond to are places, because R is curvature divided by coupling, are places where the coupling is 0. And a place where the relevant coupling is 0 is a non-trivial vacuum for the CFT, because there's no coupling, but there's a non-trivial valve. So these are symmetry breaking vacua of the CFT associated with the UV fixed point. And there is an infinite number of them. It's not important. And here is eventually the important thing one needs to calculate once you have more than one competing saddle points. And this is the free energy of these vacua. And the free energy here is computed as a function of the infrared parameter, because it's the infrared parameter that counts individual solutions. And as you see, it becomes large and negative here, but then it goes up, and it does many things here that are difficult to see, but you can see them here. These are the non-trivial saddle points that exist in this region. So, and this is in fact a blow up of the free energy near the origin, where the free the curvature is weak. And I guess that's it. Let's forget the rest. So let's now use the free energy to select which are the dominant saddle points. And for the dominant saddle points, you have to fix coupling, let's say curly R, and then find all solutions that have the same coupling, and then compute their free energy, compare, and see which one is the lowest. So this is what's done here. Here it looks a bit simple. This is free energy, but now as a function really of the coupling. And the important part is here, and it's simple. This part is not simple, because this is a blow up here, because you have many, many saddle points. In fact, this becomes an infinite number of saddle points. But these, as you can tell from here, are not important, because they are never dominant. The dominant saddle point is the saddle point, in fact, where the scale factor is monotonic. And it's the closest one to the left. So there is another issue here, which is, in fact, appearing also for theories that have ephemeral scaling and realize BKT transitions in holography, that is an infinite number of saddle points, out of which one is dominant. And in such cases, it has been seen that there is a ephemeral scaling, that is the ordered parameter that classifies the valve, let's say, classifies these fixed points, has an exponential hierarchy. However, we don't know if there is something like this here, whether it's similar or not. I don't know what you call. Efimov did the theory of weakly bound 3.3. Yes. This is a completely different problem, but the type of scaling that was found in holography in BKT transitions, in fact, is similar. That's why they call it Efimov scaling. But the problem, of course, is different here. It's not a problem of bound states. Yes. So right now, I described the dominant saddle points that correspond to starting from the UV and going to infinity. And that would correspond to a single theory on ADS space, which was confining when it was on flat space. However, as I showed you, I have also two boundary solutions which correspond to interfaces. What happens to them? Now, these two boundary solutions, I sketchily would describe them like this. They are solutions where you start from one boundary, you flow, you go to the other boundary. And of course, these boundaries touch here, as it happens if you take the slices to be ADS. If they're compact, they are wormholes like this. And the question is, in that case also, for each, in this case, you have two sets of couplings. You have one set of couplings for one boundary, another set of couplings for the other boundary. And the question is, for a given set of couplings like this, which is the dominant saddle point? Because there is always an infinite number of saddle points also in that case. However, in that case, there are also competing saddle points that are disconnected, because I can take two of my solutions that run off to infinity, and I can have a solution with two boundaries, which competes with this type of saddle point, and I have to also include this in the counting. I won't show you details, but the answer is that the factorized solutions always win. Yes, that's right. Contribution to what?
Because of the singularity.
The singularity doesn't contribute to the free energy. This is known that in confining solutions, the infrared is like a regular thing. There's no contribution to the free energy from there. It doesn't act like a boundary. So there's no way you can make a mistake there. So this is the dominant saddle point, and therefore this will indicate that if you compute a cross correlator, that is a correlator, you have an interface, you take an operator on one side, an operator on the other side, you compute the two-point function. If you compute it here, it's zero. If you compute it here, it's non-zero. The difference between these two is a finite number times nc squared, and therefore it would indicate that this correlator will be suppressed by nc squared, which in fact it would mean it's e to the minus 1 over g string squared in string theory. However, as one realizes, is that even in cases where you have in holography disconnected saddle points, there may be perturbative corrections. That is, to next order in 1 over n squared, there may be a propagator which starts here and ends up here. It has been argued, in fact, in earlier cases, although so far nobody has been able to do a computation. So if there are such connections, that means then that such correlators, the leading contribution will come from here because it's not exponentially suppressed, it's suppressed by power. But one would have to compute it to know whether there are non-zero such corrections. So in that case, it's possible that the disconnected two-point functions are power suppressed or exponentially suppressed, but we don't know which one. And it's not also clear what's the interpretation of this in the quantum field theory, although there are some ideas. Now let me come to something that I think was mentioned probably by Carlos, the notion of f or c functions. Once you have finite curvature slices, I mean, we know, for example, that if the slices are flat, there is a well-known picture of C theorem and C functions, which matches, of course, what we know from quantum field theory. So let me define this combination in the gravity theory. A dot squared, A is the log of the scale factor, and this is the piece that's proportional to the curvature of the slice. And here, the curvature, you can take it to be 0 or positive or negative, so you can have positive curvature slices or negative curvature slices. And then if you use the equations of motion, this is equal to this. Minus V is the bulk scalar potential, and phi dot square is phi dot square. And in the ADS regime, in fact, V is negative. So this is positive, and therefore F is always positive. In fact, F is never vanishing. Then you compute its derivative with respect to the flow parameter, which is the flow parameter, and the answer using the equations of motion is this. So df is a dot phi dot square, or if you compute its derivative with respect to the scale factor, it becomes this one. And this says that as long as the scale factor is monotonic, then f is monotonic. And this, in fact, matches what we know for r equals 0, because in that case, the scale factor is always monotonic, as we know, and this is the usual C theorem in such cases, which is known since antiquity. Now, if you go near a boundary and you evaluate this, this goes to 0, and therefore A dot becomes one of the ABS length. A dot square becomes one of the L square, and this, as it's well known, is proportional to the central charge of the respective CFT.
You had situations where the scale factor was oscillating.
We'll get there. When, as I said, when the slice case curvature is 0, this is the usual C theorem. In fact, if the theory is confining, in that case, FIR becomes infinity, and this is compatible with having a mass gap. It's a theory with no degree of freedom, zero central charge. When the slice curvature is positive, so if your theory is on a sphere or de Sitter, F starts at a constant and diverges in the IR. That's again compatible with the fact that you have a mass gap. Now, the interesting thing is what happens for negative curvature slices. First of all, as I showed you here, this is extremal when either A dot or phi dot vanishes. And then you can show that when A dot equals 0, and these are the 8 bounces, that's where the scale factor is changing direction. In that case, you either have a maximum or a minimum of F, but when you have a phi bounce, that is when the scalar changes direction, it's an inflection point. But the monotonicity remains the same. And in particular, it's also known that when you have a single H bounce, F maximum becomes, in fact, the minimum size of the scale factor at that point. And this, in 1 plus 1 dimension, has been related to the left entanglement entropy, because if you have an interface, you can define a very simple entanglement entropy. You take the two sides, you integrate one, and you calculate the density matrix and the entanglement entropy for the other part, and this, in fact, is related precisely to this value.
Yes.
Yes.
So the opposite limit, f going to, I don't know, 0 or 1, can it be thought of as a string, on the string defect? There is no mass gap there.
F, in general, if you stay in the ABS regime, cannot go to 0.
Okay, but away from infinity in any case, does it mean that I have a string theory?
Not necessarily, because all of this is semi-classical.
Sure.
Only if F goes to 0, you go outside of the holographic regime, and then this is the usual story that people describe in the swampland program. But I have nothing to say about that. In fact, to put different, this type of things you don't trust if you have string defect. So here are a few examples from solutions. So here were solutions which were regular, going from a maximum to a maximum. So you see this goes from one maximum to another maximum. So these are two different theories on the two sides of the interface. And in green here is this function f, which you can see separate here. This is as a function of phi, and this is as a function of u. It goes to constants exponentially when you go to boundaries, as it happens here. And it has a single maximum, because here you have a single minimum for the scale factor, and it has an inflection point. No, sorry, here there's no inflection point, sorry. This is a more complicated solution that bounces back and forth. It goes from the same maximum to the same maximum, that goes back and forth. And you can see here that you have 3 extrema, one maximum, a second maximum, and a minimum. These are places where the scale factor turns around. And then you have inflection points where phi turns around. And these are solutions now for a confining theory that go from a maximum to infinity. And in this case, you see that the f function starts at a finite point. That's the uv, and goes off to infinity, because that's is a gap theory.
So what are you plotting in the vertical axis in the upper picture?
Green is the function f. The other two is w and s, which are not important for understanding my point. But that gives you all the details of the solution. And I am finishing by answering Costa's question. What happens for these cases where the scale factor goes up and down? First of all, you see that you have many maxima and minima of the function, and then you can ask an interesting question, to which I don't know the answer yet, but it can be done rather easily, and we're doing it. How these maxima and minima are related to entanglement properties of the theory. So one would have to compute, in fact, the possible entanglement properties. And what I suspect is that the minimal one one that will give you the entanglement entropy would be the first one. Here, that remains to be seen.
So in this picture, we have oscillations, let's say 10 times,
Yeah,
then it goes down.
yeah. It goes down to the UV, this is the UV fixed point, and this is the infrared. It goes to infinity. I should say that these look bizarre from the point of view of quantum field theory, but one should remember, first of all, that these are dual to interfaces in this case, but you can make them dual also to normal quantum field theories on ADS. But the whole point is these solutions are never dominant, thermodynamically dominant. So there is no real puzzle, in a sense, in terms of this bizarre behavior. They're subdominant puzzle set. The more ups and downs they have, the more subdominant they behave. They become. So let me conclude. Let me skip that and go to a few open ends. The constructing a single non-confining holographic theory in ADS, not just interfaces, is still an open problem. We don't know how to do it. We have constructed confining theories on ADS. These are the saddle points I showed you, but not non-confining theories. People haven't studied from a holographic point of view interface correlators. It's an open problem. The other open problem is Wilson loops in quantum field theories that are on ADS in the confining case that we described. We haven't analyzed the other issue that is expected to be different in ADS, that is the dynamics of the incident gas, that will come by adding the operator dual to FF dual, which is an axiom, and studying more carefully entanglement in such theories. Thank you.
Could you put back one of the first exercises where the slots were going back and forth, balancing? Maybe the first one, yeah, that one. So you have here a three potential, correct?
You can call it like this. It's something, W is a dot, and S is phi dot for the solution.
What is multivariate?
What do you mean is multivariate? Sorry, wait. Yes. Let me tell you why it's multivariate.
So from that W, you build up the potential itself, correct?
No, I'm not building the potential. I fix the potential, and now I'm computing solutions. And each solution has a different W. It's not like in supersymmetry. In supersymmetry, you fix W because it enters your Lagrangian, and the potential is determined in terms of W.
Okay, and at the points where the derivative becomes infinite.
Which derivative?
Phi.
These are precisely the points where phi dot is equal to 0.
Then it goes to infinity with some power law, or
It goes with a specific power law. In fact, let me put it like this. These look discontinuous because we're using phi as a parameter. If you use u as a parameter, these are perfectly regular solutions. But it's the signal that the first order formalism here breaks down exactly at where phi dot equals 0. But this is not a singularity of the solution. It's a singularity of this function.
so the significance of the order that it goes to infinity?
No. This is fixed by the equations. In fact, if you take two derivatives, it's divergent. It goes as phi to the 3 halves. But that's determined by the equations. But when you convert this into the evolution as a function of the holographic coordinate, this is perfectly regular. But it's
artifact of the
expected.
description.
It's an artifact of the first order description, but in such cases, there is an argument, we haven't done the computation yet, that correlators, once you have a phi bounce, will have a peak at that point, and that would look like a quasi-particle in a theory that doesn't have quasi-particles. But that needs to be checked.
Can we go again over the oscillating A factor? And can you comment again what happens to the C function in that case?
The C function I showed you. Well, you cannot call it C function really in that case, but that's what I showed. That's the C function.
So the C function oscillates?
Yeah.
Okay. And you said that these particular solutions are thermodynamically, in which sense thermodynamically? No stress free. But they
Once they're saddle points, they can stand on their own, although in a path integral you wouldn't know how to dig them out easily, if you wish, because there would be other dominant solutions. Although some thinking, in fact, if you consider really the extreme solution, if you sit near the boundary, this has an infinite number of oscillations, and this looks a little bit like solutions that people argued in the past to involve discrete scale invariance and limit cycle.
Yeah, I remember one paper that you mentioned.
Right. And I don't know if how seriously you can take these solutions because they're thermodynamic. I think if you can find observables that will get the dominant contribution from such solutions, maybe you can discuss it. Otherwise,
Or just by factor
they
of
are
order?
suppressed by e to the minus a number times n squared. So since you are working as nc goes to infinity, they are heavily exponentially suppressed. Whether if nc is finite, we don't know whether these things are there anyway.
Even if it's 5.
Yeah, but then we don't try.
Perhaps one more question because we're getting late and
Is the analysis at equal 4 here, or the theory doesn't matter?
For what I'm telling you here, B equal 4 doesn't matter. There are details, but all of these effects have nothing to do with B equal 4. They're generic.
in interest of time, I think we should stop, even though this is very interesting. And, we're gonna, thank you very much. Let's start again at 11:30. Okay. Un attimo, I have to ask, what is your exact cut for this, or even if you have like more bumps, that will have more.
If you have more, I shouldn't think of anything.
Yeah.
Άρα τι γίνεται, Παντελή, κάτσε λίγο να κάνω κάτι λίγο.
Λοιπόν, αυτό το έχει εδώ δουλεύει. Είναι μπρος πίσω το λέιζερ. Έτσι για να υπάρχει φυσικό. Όχι, έτσι μου τα φέρνανε στην αρχή. Απλώς δεν τα έβαλα όλα για να φέρεις. Okay, I think we can start. So our next speaker is Kostas Papadopoulos from Demokritos. So, okay. Okay. Good morning. I would like to thank the organizer for this opportunity to speak here in this nice workshop, or as it's a Triημερίδα. Okay. And okay, my talk will be about amplitude reduction at two loops. So let's start. Here will be a bit the outline of the talk, an introduction. We talk about essentially a kind of continuous, let's say, evolution from leading order to next leading order. And okay, there will be some parts will be a bit more technical, as Yorgos already pointed out, but I hope we can go through. Now, let's start with an introduction. Of course, the last decade, let's say, the major discoveries, I would say, in physics, or at least some of the major discovery, it was the Higgs particle in LHC, of course, the gravitational waves, and this kind of black hole horizon study by the telescope. All of them, they require really a huge, or if you lay a large scale infrastructure in order to be able to get these discoveries. Of course, you know the LHC at CERN, the LIGO experiment, this telescope array, and the important in all these things, discoveries and discussion, is that the theory, let's say, the predictions of what we would expect, it was really very important in order to be able to do these discoveries. And this is because I don't know how much this will be, let's say, also in the future. The signals are extremely faint. And therefore, in that sense, you need a very good theory in the sense of predictions in order to be able to see what is, let's say, the deviation from what we know before and discover things. So therefore, this is quite important. Of course, I'm most focused on this kind of LHC physics, and of course there is a plan, as you know, for extending the physics at LHC also in the high luminosity phase, which will take some time, okay? Okay. And as far as the status now of things is concerned, okay, it's not very recent picture here, there may be more recent. We have in LHC really, you know, a very big number of measurements concerning more or less all possible scattering process we have. And the point here I would like to mention is that in the expected, let's say, measurements, which will be done, let's say, in the next decade, the theoretical prediction are already not very good in shape, in the sense that they compete with the statistical and systematic error of the experiment. So therefore, there is really a need to go even further in precision of the theoretical prediction if we would like to really do LHC something which is very fruitful in that sense. Of course, the next step, which is already designed, is this future circular collider, and the energy will go up to 100 eV, the luminosity also will go up, and as you can see from this table, the number of statistics will really go up to almost 1 or 2 order of magnitudes, even more in some cases. Therefore, this is really a breakthrough in the sense of particle physics, if this is realized during, let's say, this century, and will enable us to study, let's say, much more things. And the reason, of course, is the cross-sections. We know they are all increases by order of magnitudes, and therefore at 100 eV we will have a plethora of signals. There is several modes that are can be studied, let's say, in the plus and minus. You see also the Z, W, etc. production, so we can really go even further. So this all points to the fact that we need even better prediction from our side. So when we do predictions at particle physics, the main, let's say, framework is the fixed order calculation. Of course, one can think about this from the point of view of separating long and short distance physics, for instance, the factorization of these things, which turns out to be essentially the way we can parameterize, let's say, our prediction in terms of long distance physics, which are the structural functions, and the short distance physics, which are the scattering matrix elements we can basically do through perturbation theory. And it's good that we have, let's say, the standard model, and especially QCD, as a perturbative quantum field theory, which enable us really to make all this calculation. Of course, in this picture, you should realize that the part which has to do with the short distance physics, this red thing, it's a little bit the minority of what is happening, because then, of course, you have to follow a lot of other things which has to do with hadronization, Parton-Sauer, etc., which is also very important part of what we call quality prediction. And over the years, even, let's say, in the latest year, we have even lattice QCD entering in this game of getting some idea of long-distance physics. So therefore, from this point of view, the theory is entering, let's say, in this picture everywhere. So in what I'm going to talk today, I will concentrate more on the scattering amplitude calculation. And the first, let's say, chapter is this Dyson-Swinger, this is DS, recursive equation, which mainly tell us how to avoid Feynman diagrams, okay? And we would like to avoid Feynman diagrams, you will see in a moment. So this Dyson-Swinger equation essentially expresses an amplitude in terms of some amplitudes. It's a recursive equation. This first line has to do with 3-order contribution, and the second line essentially covers all loops, okay? If you can really enter in this second line, you have here your amplitude for any order in perturbation theory. No?
the final state should be the same as the original one, right?
Yeah, so you have n particles here. Yeah, so you have n1 blobs here and two.
You split
Yes.
the one blob into two.
Yes, you have some amplitudes. Yeah. So you reconstruct everything from cursive stuff. Okay, and why we would like to do this? So you see here the Feynman graphs for a process like glue to n gluon, how it goes with the number n. Okay, it's really amazing, the number which you get for 8 and 9 gluon, where with the Dyson-Zwiger equation, essentially, you get a much better, let's say, behavior.
Some empirical rule that shows how it grows.
Yes, this is n factorial, and this is a power of n. That's a huge difference. Okay, I'm cheating a bit. We will see in later because there is the color issue here. But okay, in principle, this is the comparison. Okay. Now, okay. Therefore, the three-order stuff has been resolved many years now. Let's say everybody is using some version of this Dyson-Zwiger or recursive equation, and everything at three-order. You can go even up to 20 particles in the final state, no problem. The next, of course, thing was in the 2000s, let's say the decade of 2000, has to do with the next to leading order. And here the motto is that instead of doing integrals, do integrands, as you will see. Okay? And of course, the standard procedure, which go back to, let's say, Passarino-Veldman, Hooft, and all these people, was to have your amplitude at one loop decomposed in terms of this kind of 4, 3, 2, 1 point basic integrals. We call it master integrals in this case. In this case, at one loop, these are very simple, or they are scalar integrals. And of course, for several configuration, of course, here, okay, different number of particles, different number of, let's say, masses, etc. But all these master integrals, they are very well known already for 30 years, let's say before the 2006. And therefore, this was the standard way of looking for the amplitude reduction. Of course, the amplitude reduction is quite non-trivial if you are going to use a symbolic program or anything like that. The idea was basically this one. So therefore, think about your one loop amplitude as an integral of a numerator and some bunch of denominators. And this blue coefficient here is this blue coefficient there, which multiplies the master integrals, the 4 point, 3 point, etc. So the idea was to turn this to an equation which is integrand equation. So therefore, you take your numerator and you expand your numerator in terms of denominators. And this kind of equation holds. And this was, let's say, the idea of OPP reduction. So the blue coefficients are the same. So you have to pay, of course, let's say, kind of fine. In this case, that in order to do this reduction at the integrand level, you need to calculate also this red coefficient, which, by the way, we call it spurious because when you integrate, these things cancel out and you get the same expression with the blue coefficient as before. Okay, then there is a part here which maybe you have not noticed very much, is what is not proportional to any of these master integrals. We call it these rational terms. And okay, for this rational term, there is basically two sources how you enter in the game. First of all, you maybe see here that I'm using the denominator, which is the inverse propagator, basically, with bars, which means it is in d dimension, and with no bars. So d dimension means 4 minus 2 epsilon. Here, without bar, means 4 dimensions. So therefore, there is mismatch, which account for the extra epsilon dimension of the loop momentum, which I call q tilde square. So therefore, there is an easy way to resolve this. And you can find, let's say, the extra coefficient you need. The extra integrals here are very simple because there are integrals over the extra dimensional momenta. And they are given here. Only 3 of them you need for any one loop amplitude. And this is coming out with this very nice formula, which has to do with one part of this rational term, which is missing from the previous analysis. But this is not all the case, because now the numerator, which is in d-dimension, has been written in terms of a numerator in 4 dimensions, so therefore we miss also something in the numerator. And what we miss is essentially anything explicit in terms of this epsilon, which is the d minus 4, to epsilon, or the q tilde square, which may appear in the numerator. And this defines what is the next, let's say, the missing part of this rational term, which we call it R2. So here we have everything calculated in the integrand level. Now the R2 is something which is on the integral level, okay, you see here. And the way which is, let's say, I don't know, God or nature or whatever was kind with us for this one loop business, is that these R2 terms, you can calculate all of them only with calculating, let's say, the 3 and 4 vertices, which, let's say, the contribution to 3 and 4 vertices from one loop graphs, and then every other thing, any other, let's say, amplitude is just calculated from 3-order structure, where one of the vertices is replaced by these R2 vertices. So therefore, I don't know if I'm very well explaining that. So therefore, in R2, what we do is we get the standard, let's say, one loop kind of effective action, let's say here, for 3 and 4 vertices. You don't need to go further for a renormalizable theory, and you calculate exactly as you do for the renormalization counter terms, putting everything, let's say, in your let's say, machinery for 3 others. So R2 vertices is coming in a full analogy with the counter terms. In any case, you need the counter terms to calculate, to get your renormalized amplitude. So therefore, this program has been successfully completed. So you determine the on-cell momenta through this cutting equation. You go through and get the R1 term, and then this R2 term comes with a class of Feynman which have been already computed for any theory we know, and they are okay, been implemented, and all these programs now, whatever they do, they use these R2 Feynman rules. Just to tell you that, of course, this is our point of view, but there is variance of this whole story, which accounts for this, what is called, let's say, on-cell matrix element, okay, initiated by Bern and Kosover and other people. And also there is also another variance of this, which comes with the name open loops, which, okay, essentially is a different way of doing the reduction. Now, of course, this has been already completed. By the way, here we have predictions which go even with an enormous number, let's say. For instance, if you look from the point of view of what happened, let's say, in the 90s or the 80s, about one loop doing Passarino-Veltman, this now is an unbelievable progress. We can have, let's say, one loop amplitude with 8 external particles, and this is well done, and already giving a lot of input to the analysis of the experiments. By the way, over the last 15 years, the standard, let's say, way of doing analysis at LHC is the next to leading order, okay? That was not the case, let's say, 20 years ago, where mainly they used leading order, let's say, approximation. Now, next to leading order has become, let's say, the standard for the analysis of the physics at LHC. And of course, as I said before, we need more. We need, let's say, better prediction on the theoretical side, so we have to go to next to leading order. And in that case, of course, things becomes a bit more complicated. I mean, I would say a lot of complicated. First of all, you need to get what I call here M with an index 2, which is the 2-loop matrix element. Okay, this is the 1-loop matrix element, which, okay, we know already. Here is again the 1-loop matrix element, but now integrated with 1 particle more in the phase space. And of course, you need the matrix element at 3 order with 2 extra particles integrated over them. So why you need that? Of course, you know the standard way of canceling the infrared divergences. Here you have infrared divergences inside your matrix element as coming from the loop integrals. Here you have the contribution of what is called real virtual. So therefore you have virtual with one ordering loop less, but with one particle more, and integrating over the extra particle, which is supposed to be unresolved. Therefore there is no restriction in the phase space. This will give you an extra, let's say, contribution to your infrared divergence. And the same happens here for the real contribution, where now the particles are extra two particles, which have to be integrated over the full phase space without restriction. Usually, this, let's say, when you prove this, you do this integration in d equals 4 minus 2 epsilon dimension for the phase space. In practice, there has been a lot of development in this case, and you can put this after, let's say, this kind of subtraction schemes to a way that everything is done in 4 dimensions, and you have explicitly taken out of your, let's say, expression this 1 over epsilon infrared contribution, which combined, of course, with this gives you a finite result, which is your, let's say, prediction for the process.
This formula for the cross-section is independent of the factorization, right? You don't assume any factorization.
You mean factorization for the initial state for the?
Yeah.
No, it is included here. No, it's not maybe explicit here, but it's supposed that you also integrate over the distraction function. Of course, over this integration, you have also to take into account, let's say, next to leading order contribution, okay? Like 1 over epsilon, etc. There are also infrared divergences related to the initial state.
Assuming you say lepton collider, how simple would be the life? Much simpler.
Well, in the lepton collider, you don't have the initial structure functions, but in principle, there also you have the initial photon. There is a lot of radiation there. Yes. So therefore, it's not much simpler, okay, in that sense.
You have also fragmentation functions here?
No. Here is the contribution to the process where you produce partons, let's say, gluons, and then of course, this has to be taken from a parton shower point of view, and then of course there is a lot of things. I don't have time to discuss all of them. Of course, then you have to avoid double counting, etc., in order to build up finally the full particle, let's say now, not partons, particle final state. Now, we are in a more, let's say, modest now environment, and we talk about this guy here, little loop matrix element. And we would like, first of all, to construct this. There are some standard ways of doing this. One is Q-graph. Let's say you just take all the Feynman graphs. Okay, there are many, but for processes like 2 to 2 and 2 to 3, they're still manageable, and people use this kind of thing. And then, of course, you will get some integrals. I don't have so much time to discuss about that. You need to go through, let's say, some procedure, which is called integration by parts. And then at the end, you have to get your master integrals as it was at one loop. Now it's more complicated, of course. But these master integrals are known to some extent, or you get a numerical evaluation of them, and that's therefore you do this reduction. Okay, it's not a very simple or easy way, and heavily relies, of course, on symbolic manipulation. There is this numerical unitarity, which I talked before about these on-cell methods, which was already at one loop. And this, of course, also goes through some procedure, which I will maybe describe a little later. And the fruitful thing comes out to be this kind of Caravelle program, which is doing some of the, let's say, gluon amplitudes for 2 to 2 and 2 to 3 process. And open loops is the other way, which is again using Feynman graphs. So therefore, this first and the third using Feynman graphs. This numerical unitarity is basically using a recursion also equation, like us. And here, of course, is something which you go to the tensor coefficient. I mean, is a bit different approach. But this also has been kind of progressed. Up to now, we don't have a generic solution, okay, which can go as at one loop for any arbitrary process. For our case, first of all, we need to construct the two-loop amplitude in the way we're doing through this recursive equation. Here is a bit of digression about how we treat color in the case of color particle. So this is basically an idea which is called color flow representation. So we go from the usual T matrices to something which is essentially a double line, okay, you see here, with the color flows. And therefore, okay, we use this already for 3-order and 1 loop, so this kind of procedure. For a 2-loop generic things, of course, you have to think about how to construct this iteratively. Usually this is done as at 1 loop by considering opening a loop, okay? Therefore, what you have here is something like 1 loop with these 2 extra chains attached. And if you open again, you go, let's say, to something like this, which is on loop. If you go to open this, it's a 3-order structure. So therefore, you use the same machinery to construct your amplitude. Of course, this had some complication at the loops, which were not present before, has to do with the color structure, but okay, this has been resolved. And we have, let's say, the way, so this is a typical, let's say, contribution written in a way you cannot understand, but I'm just telling you that this is the way that the program takes the information, and here, taking this information, construct, let's say, numerically, the integrand of every contribution we have in the 2-loop amplitude, okay? And by the way, this kind of, let's say, construction, which is very simple, I mean, from the point of view of numbers, there are integer numbers here. The integer numbers here basically describe which thing you have to connect with what, and what are the colors, what are the vertices you have to use. This kind of structure we call the skeleton is nothing to do with D. I mean, you can use it basically even in D equals 4 and D equals 4 minus 2 epsilon dimension. This is kind of important. Now, this program has been, let's say, the HELAC program at 2 loops has been completed in a very first prototype, and we have also results about matrix elements at 2 loops and how many contributions you have and how many time you need to construct them. But this is okay, but the main thing is this integrand reduction problem. And
The slide before is only the integrand. That's how big your integrand is. It's not
the integrand.
No, the table. This table only tells you.
Yes.
Outside
The full amplitude. The full amplitude is composed in different contributions. Each one corresponds to an integrand. And you see here there are many of them. Okay.
No, but I'm asking. This is not integrated.
No, exactly. Of course, this is just the structure. Yes. This will allow you to put the numbers, let's say, for the external momenta, the polarization, and get a number.
What's the last column?
You see, in our rates, we don't see this. So it's the number of this contribution, let's say, this kind of contribution, how many you have for, let's say, gluon to gluon. So it's 4,000. For, if you take full color, it's 89,000, etc. So it's this number of these packages.
And may I also ask, you said you construct the integrand numerically.
Yeah, I mean, when you have this kind of information, then you just put, let's say here, let's say this is the wave function of a gluon, which is another gluon, and this is a vertex. So you have all the structures. So you take line by line, and you get numbers. Yeah.
So you mean you evaluate the kinematic parameters of your amplitude?
No, you can evaluate the amplitude for a fixed external and internal momentum.
And internal momentum.
Yes.
So every time, so if you are to integrate it, you will have to do this for every integration point.
And this kind of integration is only tried by the group in ETH, by Babis, not in this form, and this is another story. I'm not.
Yeah, I'm just trying to understand. So indeed, one has to do this for every integration.
No, but we are not going to do that. We would like to have, an integrand reduction.
Okay.
So therefore, this kind is turned to something which is at 1 loop is master integral time coefficient. So therefore, the program at the end will calculate the coefficient, and will take the master integral from somewhere else and get the full amplitude numerical.
Basically, that's your unitarity where you put the 3 and you glue them all together. This gives you like a number, and then you want to compute this number equal to some ansatz. And
Yeah, exactly. We will see that. So I hope even the experts have questions. I hope you have questions. Please let me. So now the integral deduction essentially goes back like what we did here. Okay, this is not basically any different in philosophy. So here we had, we have a numerator, and we try to decompose in this kind of way. Okay, and as I told you, this blue coefficient, they are all depending on the external momentum, nothing else. This red coefficient, they do depend on the loop momentum, but they integrate to zero. So this is a very simple, let's say, way of looking at one loop. But unfortunately, of course, at two loops, this is not so simple anymore. And now what we have is in the numerator something. We have a bunch of propagators, let's say inverse propagators in the denominator. And essentially, we have some kind of kinematics. Now, the kinematics is even more complicated, of course, that one loop. You have the external momenta, P, you have the internal momenta, K, you have also some, let's say, transverse space over the external momenta. And all these kind of things, they are going to be called the Z, let's say here, and include, which in the jargon we are using, they are called, let's say, what is left here on the numerator, let's say, is what is called irreducible scalar products.
So what are the etas?
The etas are the transverse space. So etas times the external momenta is zero. So for instance, if you have three momenta, like in 2-2 process, there is an extra momentum to cover the 4 dimensions, which is transverse to this P1, P2, P3. Of course, if you have more momenta, you don't have transverse space because the momenta covers all your. Okay, the basic idea is exactly the same. So we would like to have the numerator put in a form where on the right-hand side, you see the inverse denominators coming into decay, as before, okay? The only thing here now is that these P are not anymore in this nice form we saw before, some blue and red coefficient, okay? In principle, these P, they are polynomials in this so-called irreducible and transverse scalar product. So therefore, this P, they are not, let's say, just, let's say, something which depends on the external momentum. It still depends on internal, let's say, on loop momentum here in this here. This is, of course, to be expected. The experts, of course, they know that at two loops, the master integrals are not just scalar integrals as we have in a loop. So therefore, there are integrals that have numerators which carry on loop momentum. And this is unavoidable at two loops and even at higher loops.
What is the basis of the loop? What is the analog of?
Yes, so it depends on the topology. So this is coming from the IPB reduction, which I think I talk a bit later. So therefore we have, let's say, this funny thing which happens, it's known for 30 years, 40 years now, that at two loops, you have, let's say, your arbitrary, let's say, integral, which composed by denominators and by some numerators. And then the IPB equation is just the fact that if you differentiate your integrand with respect to the loop momenta and integrating, this should give you zero in dimensional regularization. And therefore, you get a lot of relations between different, let's say, type of integrals at two loops. And somehow, miraculously, this happens to be reduced, let's say, an infinite number of integrals are reduced in a just subset of master integrals. So for instance, for a 2-to-2 process with massless particles, there are only 8 master integrals.
Is it known for arbitrary solutions?
This is a bit tricky. First of all, this IPB equation starts to be more complicated if you put masses into the game. So I would say that, let's say, keep low profile in a sense. And if we talk about the main process we need to calculate, let's say, for 2-to-2 and 2-to-3 process at the LHC, a lot of these kind of bases are known. And of course, you can get everything from, let's say, this IPB equation, even for higher point functions, but at the cost of, some time and computational resources. Everybody believes that there is.
Are there mathematical proofs?
Yes, that's what I'm saying. There are mathematical proofs, but okay. Let's say that yes, this is the consensus that.
So who did the theorem?
Look, several people. I mean, basically, all this started from the Russians, so therefore, I would say the Russians has the idea about, I don't know, maybe Yorgos knows, but I think that, yes, Smirnov, and Smirnov, and Smirnov, I don't know how many generations of Smirnov. But okay, this is not a very big problem. The problem is that, okay, it's one thing to prove that there is a finite basis, which, okay, more or less you can do it with several methods. It's not something very difficult. There is also this Baikov representation of the integrals, which also helps you to understand this problem, which has to do with algebraic geometry after that, okay, the critical points of the integrand, etc. But the point is that to work out the IPP equation is a very long story. So it's for 30 years now, it's a Laporta algorithm coming from an Italian, let's say, colleague, which is quite very exhaustive, let's say, very, very complicated and very computationally with the resources. Okay. So therefore, this is one problem, but let's say the important thing here, which I would like to mention, is that here, this kind of coefficients, the polynomials, let's say, they are not so simple as it was, let's say, at one loop. They have dependence on the loop momenta, which is, after all, needed. There is no way to avoid that. And therefore, at the end, your, let's say, stuff will be given by this kind of polynomials. Let's say you have monomials, which is made up from irreducible scalar products, and then some powers, and this will give, let's say, the full stuff. Okay, I will not go. So at the end, therefore, of this procedure, when you have all this, let's say, equation, you can think about turn it to something which is coefficient times master integrals. How you do that? In this polynomial, there are coefficients which depend on the external momentum times monomials of loop momenta. This turned out to be in this form. Okay, any monomial can be turned to a inverse propagator. For any topology, there is a specific number of momenta, let's say monomials, let's say scalar products, which describe this problem from the kinematic point of view. So let's call this that this is the number n, is the total number of this kind of thing. Some, they appear in the denominator. We call it reducible scalar products. Some in the numerator, they call it irreducible scalar products. In any case, these are the integrals, which after that, through this IPP equation, they turn out to be just rational combination of master integrals. So therefore, what we are basically trying to do is exactly to get this kind of reduction. So to calculate these polynomials. And okay, I'm not going, since I don't have so much time, too much, but in principle, if you work in d equals 4 minus 2 epsilon dimension, everything goes through, and you can get your, let's say, reduction. And this is, okay, this is simple in a sense. But of course involves, except these 8 components of the 2 loop 4 momenta, also this kind of extra, let's say, d-dimensional components of the k1 square, k2 square, and the k1.k2, which call mu here. Okay, this can be done. This is not a problem, but we would like to have a numerical approach to this. So therefore, to get all this coefficient numerically. And then if you try to do this in 4 dimensions, you start getting some problems, because in 4 dimensions, the monomials, let's say loop momenta times external momenta, they are not all independent. There are special relations, which comes out with the Gram determinant, of course. And you have to find a way to do this thing. Okay, we started this for several contributions, and we try to do it systematically as much as possible. In some cases, this go through. In some other cases, there are still some technical issues which kind of work to resolve. Of course, to work, as I said before, in d equals 4 minus 2 epsilon dimension, this kind of problems are not there. And in fact, in that case, you don't need to have separately calculating the R1 and R2 terms, this rational term we discussed before. And that comes to my final, let's say, thing, which is, can we get this dimensionally regulated numerator, let's say, including this epsilon part from, let's say, numerical perspective. Let's say, can we do this on a numerical, let's say, basis? And the answer is that people, they try. This, the numerical unitarity program, relies on imposing that the particles that are inside the loops have dimensionality which is more than 4, and therefore they go to some higher dimensional for the internal gluons, quarks, whatever. And there is also some approach to use extra Feynman rules to get this thing. In our case, what we try to do, and I will go a bit fast on that, we try basically to write down recursive equations with, let's say, the way that the extra terms we have, let's say the extra currents in this recursive equation will produce exactly this coefficient of these terms we need. So just to give you a very quick idea is that whatever you look at your amplitude, you have a loop momentum square. This is one loop. You have also to get a term which is proportional to the epsilon dimensional part, which we call the mu. Whenever you have the polarization vector of the two internal particles, let's say gluon, you have to get also this d minus 4, because this lives in d dimension. And whenever you have this, you have to also get this extra mu term coming from the multiplication of this rule. So therefore, this in principle is simple, and you can extend it also to higher loops. The fact is that your original, let's say, recursive equation, which goes with this current, and which follows, of course, the standard rules, there is nothing here special. You need to add new currents, you see here. Of course, all of these currents, they do satisfy recursive equation. Now, talking about currents, okay, sorry about that, but I have to go back in the very beginning where Elias asked the question. Okay. Sorry, this is a current in our case, because this is an off-cell leg. These are knee on-cell legs, so this is another current. So this is a construction current recursively from currents, okay? Okay, no, that's just algebraic. Whatever comes here, we talk currents here in the sense that this is the amplitude, okay? The construction of the amplitude.
You have an external line.
All there are knee external lines and one here which is off-cell. Okay, there is nothing, you know, conformal field theory currents. There are some amplitudes, okay, if you like. So here you see that therefore the sum amplitude with n particles comes with the sum amplitude with n1 particles and n2 particles through the standard, let's say, vertex plus some contribution. So therefore you need more, let's say, ingredients to get out your results, but this is doable. So in the expense that you get more recursive equations that we have before, you are able to construct the full numerator in d dimension. And the important thing here is that all these coefficients are taken through a numeric evaluation. So therefore, you know, so you can put, let's say, the mu value, the extra, let's say, epsilon dimension part of Q, and also you get this coefficient numerically, which is multiplied by d minus 4. So therefore, this reconstruction is possible. And we are doing this for two loops now. So at one loop, we have essentially seen this already done for many gluons. And now we extend it to two loops. We have already basically done this for two loops for gluons. And what is, let's say, the point here? If you know how to do this calculation, then of course you don't need to have explicit computation for these rational terms, because now everything is in here. Okay, here is the full numerator. Okay, in the dimension. So you don't need to do anything like what we did before. Of course, at one loop, this kind of lucky situation with the R2 terms and the fact that we can calculate R1 term, as I said before, from the integrand, it may be, let's say, more effective with respect to these things. We have not really tried that because the one loop was kind of a stop for us, you know, some kind of intermediate, let's say, stop in order to extend this at two loops where really we need this kind of story, because as I said, at one loop we have already the machinery. At two loops, though, this is still missing. So therefore, just to summarize, we have a construction, let's say, at two loops. We understand, let's say, how to do all the integrands that contribute to an amplitude, and this, of course, through this Herlach framework goes to any arbitrary number of legs and any arbitrary number of configuration. There is no limitation here, apart, of course, from computer resourcing and the fact that we deal with a complicated, let's say, problem. The cut equation is now working, and basically we can do this for on-cell loop momenta. And okay, as I said, in D equals 4 minus 2 epsilon, this is something which is quite interesting. Integrand-based construction. Now these polynomials I showed before in this, sorry about that, here, these polynomials have to be parameterized, and the fact is that we know how to parameterize this. So it's called integrand basis. And well, as I said, at one loop, this is already working normally, and at two loops already solved a lot of problems. We are now to understand a bit better this d equals 4 and d 4 minus 2 epsilon reduction, okay, in practice, in order to be able to implement it in the numerical code. And so, of course, the IPP reduction table is still something which comes from outside and has to do with the reduction of the integral to master integral. And of course, the master integral numerical evaluation, as I said from the beginning, from the Costas question, there are not all of them known. There are a few of them known. And of course, for these processes where the master integrals are known, this program will give you the amplitude numerical evaluated. Okay? Yeah, that's it. Thank you. I would say topology specific.
Yes, topology,
okay.
Yes. Topology, how many external legs, how many masses,
I mean, left for the audience to say that what I mean by topology and what we mean here is that we have, let's say, what kind of particles are around, how many, first of all. What kind, I mean, let's say we have on-cell or off-cell, and what kind of masses you assign internal. So this kind of describe a topology, okay?
Yes.
So this applies to many processes, not only one process.
I agree. I mean,
Yeah. Yes, okay.
Exactly. Total number of particles, how many are masses, and so on. This means that then the analog of these C coefficients for one loop is also needs to be adjusted to the particular case of master integrals for this process.
Of course.
Does this relate to your very last bullet about the
no, really, yes, okay. No, I think you can understand but I don't know if the audience. I mean, here you see that I write the amplitude in terms of coefficients, which are depending on the external momentum times this f, and this f are these exactly integrals, okay? And then, of course, these integrals by themselves, they go through IPP to some other coefficients, which still are rational and depending on the external momentum, times the master integral. So therefore, here at the end, what I'm saying is that essentially this last thing, let's say this IPP reduction table, yes, this is still something outside of us. I mean, we will do it for a given topology from file, taking tables, and then when we come to our, let's say, reduction, the integrals we have will be transformed through these tables to the master integrals. Yeah, but this is not something we do. I mean, essentially something which is done by external, let's say, resources. No, we have to implement, of course, yes, but yeah.
Just to understand better maybe Theodore's question. Okay, at one loop we know we have this Massarino-Veltman basis, right? It's A, B, C, D, E.
Yes, thank you. I would say this basis is known from Tkuft. I mean,
let's call Massarino-Veltman.
Yeah, okay. Yeah. Because Massarino-Veltman has to do with the reduction, okay. Yeah.
Now, this is at one loop. After two loop, probably this has to be extended, right?
No, no, it's as I said. I mean, every topology. So there are many topologies. So, for instance, if you go to a 2-to-2 process, you can have everything massless, everything outside on cell, but you can start then putting one particle of cell. So it's another topology. A two particle of cell is another topology. Some masses inside, there is another topology. So there is really a huge number of topologies, which every topology has its own master integral. So therefore, the number of master integrals is increasing. Okay.
But we do know that it's finite.
Yeah, that's we know. Yeah. And
But we don't know how many there are.
No, we know.
It's case by case as far as
No, we know everything, how many there are, etc. And we can make tables about that. But I'm saying this is a procedure which is not, look what is the difference here. At one loop, all this kind of box and, okay, where is that? Here. Okay. Here the box is not one integral, okay? It's, you know. I mean, no. Apart from I mean the scalar integral, it's not one integral. You can have any kind of invariant mass here, let's say, of cellness. You can have any assignment of masses here, okay? So if you count, there are many different, let's say, integrals here. But they are all in the same category. They are scalar. Yeah. Yes. No, it is not the same form. They have different expansion in dialogues, etc. So it's not the same form. Some of them, they are, let's say, infrared divergence. Others, they are not. You know, it's a very, but okay, we know all of them. It's not so many, you see, there are just 4 propagators here. Yes, yeah. And we know explicitly all of them, okay? And at two loop, we also know explicitly the integrals we know. But of course, this is a construction which is done topology by topology, depending which topology contributes to your scattering amplitude.
Okay, so what I need after time, 2 more questions.
In any proportional diagnosis where people are trying these techniques, people can do higher loop computation.
Yes.
Can somebody do today, let's say,
Yeah, okay. Yes, okay, one moment. The point is that at n equals 4, okay, I'm not very much an expert. Maybe George can help here, or Alessandro. The fact is that in this kind of very symmetrical theories, many of these things are absent. So you have to have only a few of them to calculate. And also, there is also the trick, which is also important about the colors. So therefore, you just take planar graphs, because this is also helping for higher orders. And therefore, yes, in that sense, you can go to higher, let's say, orders, okay?
the question is
But one moment. Higher orders for, let's say, process like 2-to-2, or 2-to-1, or 1-to-1, let's say, not for what we need here. Here we talk about 2-to-n, okay?
Yeah, but let me take any 3-loop. Is there any 3-loop algorithm that has been so far computed?
Yeah.
In,
Yes, of course, of course. I mean, first of all, our, let's say, friend, okay, Babbage has done this for 3 loops for Higgs production. Is 2-to-1, let's say, in a sense, okay? Right now, there are many, I don't know if Alessandro will talk about, yes, for 2-to-2 processes at 3 loops, okay? So there is a lot, but let's say, from the point of view of, let's say, practicality in the sense of LHC physics, it's not very clear that this is the way we should go. Because one thing which you don't need to, I mean, you have not to forget is that here you have to combine several contributions, okay? And this is very painful. It's not very simple. Now, if you go to 3 loops, this lines becomes even more, okay? You have, let's say, RRRR, RRV, RVV, whatever. And this is not work for 3 loops. So therefore, even if we know some amplitudes, we cannot really do anything practically, physics. So therefore, in that sense, maybe what Babbage is doing, which is trying essentially to get the amplitude itself in loop momenta and integrate in the loop space, which of course is terrible, okay, because it suffers from a lot of analytic problems. This may be something which scales better.
So when you write the integral as coefficients times, yeah, the amplitude actually, coefficients times the integral, it's only coefficients that depend on polarization temperature.
Yeah, yeah.
So I guess the integrand is independent.
Yeah, of course, yeah, of course, yeah.
Which means that we can just generalize.
Yeah, that's what I said. It's topology and not specific to an amplitude. Yeah.
Thank you. I would like to thank the organizers for inviting me here. It's always very nice to be in Athens, not in the summer, but in the winter. And so today I'll present some not so recent work, but if time permits, I will present some more recent work done in collaboration with Benjamin Bassot, which is at ENS in Paris, Artur Clemencio Suero, who is a PhD student in Paris, and then some more recent work done only with Benjamin, where we try and understand a bit better how can we compute structure constants from integrability. I will mostly focus on n equal 4. Whatever I say can be hopefully in the future extended to actually other theories. And with this, let me discuss a bit the plan of the talk. So I will introduce, between inverted commas, it's a very brief introduction about integrability, what it is, if people don't know, and I will focus mainly on n equal 4. And then what I'll try to do, which is a difficult task, but we'll see how it goes, I'll try to present some conjecture that we came up on how to use hexagons, which I'll explain what they are, to actually study short operators. All of this will be explained. I will discuss what we did to test our conjecture in the weak and holographic limit. And then I will try, if time permits, discuss about this new line of work with Benjamin, which is when we try and study this small spin limit and what we were able to learn from the small spin limit of these structure constants. Very well. One-page introduction on integrability. Well, as you have heard probably from your classical mechanics course, or if you've done any analytical mechanics, it's practically, if you have charges, it's very nice, and if you have as many charges as degrees of freedom, then you can actually completely fix your motion of whatever particle, whatever thing you want, just by constructing this, just by these conserved quantities. In principle, what people say is that you can solve everything by quadrature. And the idea is that for sure you've seen this is like a player motion. You have like this particle in a central gravitational field, moves around. Okay, what do you have that is conserved? Well, usually energy. You have the total angular momentum and then the angular momentum in the z direction. So everything needs to be on a plane. You plug in this tree. There is some nice framework where this works, which is I think Liouville integrability, and then you write down some simple equation you can solve and obtain directly without having to do any complicated study of, okay, what's the force, what do I have to do, what to think about. Just a machinery that gives you this. Of course, it gives you an integral, and you need to be able to solve this integral. This is a secondary problem that one needs to specify. So this gives you a solution, but then you need to find the solution, which is always complicated. Actually, the Kepler motion is even nicer than integrable. It's called what is called super integrable, because you have more conserved charges than actually degrees of freedom. You have also this, it's called like, yeah, Laplace-Runge lens vector, which is an extra thing that allows you, I mean, it's super nice. What happens if you want to do this in QFT? Well, in QFT, you have technically an infinite degree of freedom, so you need an infinite set of conserved charges. Okay, this is a bit of a weird idea, but you can think of it as some sort of like infinite, this infinite set of conserved charges. They need to commute with your Hamiltonian and all these sort of things. And people have used this in several places. Mostly in 2D, because you have a theorem that tells you that if you have an infinite set of conserved charges that they commute, I mean, your scattering is trivialized in dimension greater than 2. So if you want particles to scatter and then study them with this infinite set of conserved charges, you can only do it in 2 dimensions. This actually leads you to a lot of nice things, which is there is no particle production. If you have integrability, or if you have this infinite, you can prove this, and then there is also that your scattering factorizes. What I mean by factorizes is that it gets you this very nice equation, which is known in the literature as the Young-Baxter equation, but it tells you that whatever, this will be like a 3 to 3, but the 3 to 3 get actually factorized in 2 to 2. And of course, you have a freedom of choosing how you want to do this 2 to 2 factorization. And the idea is that this actually, by only solving this equation, you can find this the S matrix or the R matrix, depending what are you trying to solve. But anyway, the idea is that everything is encoded into this function that you can find. You can bootstrap from this equation, and you have practically solved all your scattering in 2D. Again, solve is a big word, but I mean, you have some idea on how to find all of this. Okay, why am I saying all of this? Well, because people have found in 20 years ago that actually integrability appears also in n equal 4. Now, let me give a brief introduction to what is n equal 4. N equal 4 is a supersymmetric Yang-Mills theory in d equal 4 dimensions, has a gauge group which is SUN, and has also a very nice property which is actually holographically dual, has an holographic dual. What do I mean? I mean that there is a string theory that lives in an ADS5 cross S5 space that actually there is a weak to strong connection, for which if I study weak coupling, if I study strong coupling of this conformal field theory that lives on the boundary of this ADS space, I can actually extract, if you want, can be actually studied by studying weak coupling of the gravity theory that lives in the bulk. Okay. That's to say that this theory has a lot of nice properties. Most of them is that actually has a huge symmetry group, which is not infinite, but can be, actually people have found that there is an, this is a bit technical, but anyway, there's an extension to this symmetry group that properly gets, becomes infinite, and there is an infinite amount of conserved charges that we can find. And for most of my talk, I will not care about this full group. I will only care about a subgroup, because things are complicated enough, and I only want to look at simple things. And so I will care about practically of the myriad of fields that are inside here. So I have one gauge field, 4 chiral and 4 anti-chiral fermions, and then I have 6 scalars. I will look at some complexified version of a scalar and some derivative acting on this scalar. So this is the only fields that will appear in my study. I will explain a bit why, mostly because anything else is, I mean, you can generalize out, but I mean, this is the nicest sector that you can have. And the idea is that this is actually a super conformal field theory, so the beta function vanishes to all loops, which means that actually this theory is even nicer than we expected. So I only need, in principle, only 2 quantities. One of them is the anomalous dimension, the other one are the structure constant. And okay, so what I'm telling you is that this theory is super nice because has an holographic dual. It's actually a SCFT. And now if I take a limit, which is called the planar limit, so if I take the number of colors to go to infinity, actually is also integrable. So this is the easiest thing you can think of, and this is why people like it so much, and people really want to work in this theory. The idea on how integrability arises, I can give you some like heuristic picture of why. Well, first of all, how it was, I want to say discovered, but understood, is the fact that, okay, when you are in this planar limit, you only care about things which are like traces. And of these traces, there are like a lot of operators inside. Okay, in our case, will be only Z and Ds. And people thought, oh, this looks a lot like a spin chain. Can I map this to some spin chain? Well, you can. And then they found that actually there is if they want to study the anomalous dimension, so this is extracted by studying the dilaton operator acting on this operator, you can find that is exactly the same as solving a problem in a spin chain where you extract the energy of your spin chain. So there is a one-to-one map between these two things. This picture fades away at some loop order, so it's not actually true to all loop orders. People wanted it to be true at all loop orders, but there are some effects that actually break this picture. The more like, I would say, the more like reasonable idea is that you can think of it as I said, there is like a string theory attached to it. So you can think of some worldsheet theory where you have your excitations, which are living on one boundary, and they, interact on this worldsheet between this S matrix that is known. And then this is more or less the idea where you can think of, oh, I need to have a 2D sort of theory. Where is it? Okay, it's on the worldsheet if you want. This is some heuristic way where you can see like this lower dimensional theory appearing. Very well. Okay. So why do we love so much n = 4? Well, because we can actually solve most of things, and at each, like this is, let me stress this effectively. People have found, I think 10 years ago, that you can actually, for whatever single trace operator you want, there is a mathematical framework which is called the quantum spectral curve. It's a complicated thing, but let us just say that is you input the quantum number of the state that you want to study, and this spits you out the anomalous dimension. And it does this in a very efficient way. So for example, people are able to compute the anomalous dimension of some operator. I think in this case, this is the Konishi operator. It's some operator in MR theory up to 11 loops. They just press shift enter on Mathematica, and it gets you out the 11 loop result. This is amazing. Otherwise, they can also compute the structure constant for operators at finite coupling, meaning that I can plug in and I can look at different values of the coupling. Of course, this is done numerically. And I can practically, I can look at whatever value of G. And lately, meaning this June, they actually found a nicer way of computing the strong coupling expansion. So I've literally control over the anomalous dimension of this theory, so of the energies of these spin chains, if you want. I have control over all the possible coupling, that value of the coupling that I would like. Okay, this is amazing, and it was a very nice result. And this QSC is a fantastic framework for doing this. funny enough, people are still studying this because you can also study different expansion in different regions. So you can, practically what you can do is that you can analytically continue some of your quantum numbers and extract other, particularly look at different operators in your theory. Very well, so this is one of the 2 bits that I need to know, okay? I need to know the anomalous dimension, and I need to know the structural constant. What happens for the structural constant? Well, structural constants are a bit more complicated. They require 3 operators, not 2, so it's a bit more difficult to make them work. But people have computed in perturbation theory using Feynman diagrams up to 5 loops, which is, I think, to my knowledge, the higher loop that has been computed in n = 4 for the structural constant. I think 2 weeks ago, some people have used the fact that n = 4 is what's it called, CFT, plus the fact that we know the spectrum so well to actually do some sort of bootstrap plus integrability, for which, and they were able to compute, I don't know if you can see it here, maybe the plot is, but they were able to compute practically the structural constant of the Konishi to very, to practically to, I think, error of, I think 0.1 to from weak to strong coupling. This is amazing. Of course, this bootstrap approach gives you access to the lowest operators. So it will be maybe difficult to extend it, but it's amazing that we are also able, in some sort of sense, for some specific operators of our theory to actually go from weak to strong coupling. So this is another of the perks of being theory integrable and actually having the access to the full non-perturbative spectrum. The idea is that, okay, what can I do in strong coupling? Well, in strong coupling, there have been some recent papers by Aldai and other collaborators where they actually studied some Virasoro-Shapiro amplitude. This is some string theory amplitude, and from there, they were able to extract actually structural constant as strong coupling. So all of this is very nice, very almost, I would say, systematized, but has nothing to do with integrability. So what I would like to present today is a method that hopefully can do the same. Well, cannot do the middle one, but hopefully can do the same as the first and the last point. So weak and strong coupling, but in a more like integrable framework. So I would like to, as there is the QSC for the spectrum, there is an analogous object for the structural constant. Well, the answer is yes, and let us try and understand how this comes about. I'm sorry, this is going to be a bit technical, but I hope the idea will come across. So the idea is that, okay, I want to compute structural constant. Let me start from tree level. And people have done this, I think, in the 2010. This is Vieira, Gromov, and they have tried to solve this problem in a similar way as they had done for the spectrum. The idea is that, okay, I need to construct all the possible weak contraction between my field, and this will give me, this is some combinatorial factor that will give me the value of this structure constant at tree level. They were trying to do this in the canonical way, and then trying to use some integrability, writing this as some sort of wave function of some, practically using some integral representative of this object, but actually they were seeing that this is not the best way to approach this problem. They see that actually this grows for very large operator. This is a very cumbersome thing to do and to implement. And they were like, okay, maybe we're not using the full power of integrability. And they found that actually they could do better by using a different approach. So when you have a state in your spin chain, you can actually do something which is very funny, but you can always represent it as a sort of entangled state. So you split your state into 2 bits, one that you call the left and the right state, and then you give some function h that practically tells you how you need to, split your physical excitation from one to the left and to the right side. They were like, okay, let us try and do it in this way. Then, of course, since here you have practical bra, you also want to have a cat, and so they invented some other method of flipping these states. And then they were, okay, very well. Now we have a way to represent our 3-point function as a combination of this left and right entangled states, and I have like 3 of them. I need to practically now glue them all back together. And this is done through something that they call sewing. Practically is using integrability by computing these norms of these 2 different states. This is known how to do in practically, using integrability. This is known how to compute this sort of bracket. And what they found is that actually this was a better growing way, if you want, this for depending on the dimension of the state, this grows better than actually trying to do the naive thing. And they were like, oh, okay, maybe, we can take this idea of the fact that I split my 3-point function into 2 pieces, and then I construct these 2 different pieces, and then I glue them back together. Maybe I can extend this idea to higher loop orders. And this is practically what I would like to present today. So the idea is so of course I need to focus on a particular structure constant because maybe it's not extremely clear to everybody, but this structure constant have also some tensor part, and this complicates a bit the story. So if you have three operators which are spinning, you have also all the different possible types of structure that can appear. So what you want is that you want only one operator to be spinning, so one operator to be non-protected, and the other two you want them to be special operator. In some sort of sense, in a spin chain sense, you practically what you want to do is that you want to have one operator to be excited, if you want, or one operator to have things which some excitations or some waves that go through in this state, and the other two you want them to be some sort of vacuum state. Okay, so this is the simple setup for people who know supersymmetry is practically having one non-BPS and two BPS states. Okay, perfect. And what they found is that this further simplifies. So I don't have to account for three swing, only need to account for one swing for the non-BPS state. And they found that actually practically there is some, as you expect, there is a combinatorial formula. Okay, up to some normalization factor, you have something that, okay, this is a partition of the two roots. So I mean, I need to split them on the left and the right. And I get these two bits that they call hexagons for a reason that will be clear in the next slide. And they said, okay, perfect. This is what we get at tree level. Would this work also at higher loops? Well, it does. Otherwise, I would not be here talking about this. So the idea is exactly this. I take whatever I take my my 3-point function and like looking at it in some sort of like worksheet way. And then what I do is that I need to split it, right? I need to cut it. And this cutting is exactly practically open it up on these three seams. And then I obtain these two building blocks that they called hexagons. And this is practically the object that I need to construct in some way. So how to do this? Well, you can bootstrap it knowing its symmetries. And the complicated problem is then gluing it back. So now I can construct these two single things, write as many excitations as I want inside, glue them back, and then I obtain the structural constant. Yeah, of course. Yeah. I mean, yeah, I was just trying to give. Yeah, I mean, if you want, yeah, I mean, as you do for the anomalous dimension, you think of it, you know, as like this cylinder where your state evolve from one point to another. In the same way, you can think of it as like this pair of pants in the dual picture. Mostly, this makes clear the fact that there is a 2D worksheet and there is integrability. Yeah. 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 Is it completely? I mean, we're doing like n equal 4, and there's, I mean, how to say? Yeah, there's no moduli, no problem. I mean, yeah. Yeah, no. Yeah. No, it's fine. It's not a problem for this, but I will explain that there is some problem by the fact that the pair of pants are small. So this is the problem. So if the pair of pants are small, then you have something which is known in the integrability picture as finite volume effects. So in principle, like all of this that I'm explaining works really well if your pair of pants is huge. Like if you have like a huge pair of pants, then there is no problem of having effects from the fact that you can have like modes that are excited in a transversal plane than the physical one where my excitation live, and these things can wrap around my pair of pants if you want, and this can give me some correction to this picture. So this is what one needs to solve. So this is one of the problems of this picture, and I will show how we did solve this problem in using some building blocks from the QSC. Let me also stress that actually this hexagon is more fundamental than to 3-point function, because actually you can use it to actually reconstruct higher point function. So if you have a 4-point function, you can glue 4 hexagons together and then you can reconstruct a 4-point function. If you have non-planar, in principle integrability is only for the planar theory, but these hexagon building blocks can be used in a very complicated way, which doesn't make the computation easier, to, for example, tessellate a genus was surface. So for example, if you have like a cylinder with a hole in the middle, you can tessellate it with these objects fundamentally, and then we can reconstruct 1/n correction, which is usually not accessible through integrability, via integrable building blocks. So this is why this hexagon is so nice. And as I mentioned, okay, we're going to look at this particular type of operator where we have some derivative to some power s, which represent, okay, the spin, if you want, of my non-BPS state, and then I have these three lengths. Okay, yeah.
So can I think of the hexagon as a 3-point vertex constructed out of the spin chain?
Ni. Which is, I don't think there is a spin chain picture for the hexagon. You can think of it as some sort of form factor. It's a form factor if you want. You have these two form factors, you glue them back together, and you obtain your 3-point function. In principle, the picture that you have is like if you have two vacuums living in the spin chain, and then you have an excited state in the middle, which is this non-BPS. This is like the best picture you can have in this sort of SOV or yeah. Okay, very well. So what are the scales that appear in my hexagon? Well, first of all, I have, of course, the length of the three operators, and then I will have like I will have like lines that represent a sort of weak contraction between my different operators. And since I'm gluing back together, particularly I'm inserting some resolution of the identity when I do this gluing back, the more weak contraction I have, the higher the energy needs to have my my particle when I put it here to glue these two bits together. That means that the higher the length of these three bridges, the higher the loop order in which this contribution will come about. Okay, so let me repeat exactly what we need to do and how this formula comes about. So it's the fact that, okay, I have these two hexagon, I construct these two hexagon, then I need to populate them with all the different seams where I've glued them back together with some mirror particles, which are some specific it's a way of writing this resolution of the identity if you want, and now I need to glue them all back together. And of course, these particles need to have will have some particular energy, and as I mentioned, this energy needed to glue this back together will be proportional to the length of these three bridges. So one thing that one can see directly is the fact that, of course, if I take this L to be infinite, well, practically I'm suppressing all the possible effects that come from gluing back together. So at the end of the day, this gives me back the same three-level picture. So if I study very, very, very large operators, so operators that are the scale of the length that the scales as G, or operators that are very, very large, I practically get back the same three-level picture that I started with. But if not, I need to be careful because I need to reinsert these things. And I just want to stress this is a very complicated thing to do. I mean, it's not super clear here, but this is practically an infinite sum of an infinite product of an infinite sum. So this is like a very complicated thing. It's not if you want to do this at finite coupling. And okay, so people have tried to do this, and I will explain how this works in the next slide. But let me just say that they have found that actually there is this hexagon integrand actually takes a factorized form, and I will explain how this factorized form look. And that's mostly it. And there is some normalization in front, which comes from, as I said before, the fact that your non-BPS state needs to be normalized. Okay, very well. How does it look like? Okay, let me do this for example, for Konishi, okay, which is the lowest operator I can think of. Okay, and let me do this pictorially. So as we said, the first step is, okay, I insert my excitation, my physical excitation in my two hexagons. I split them. I have this sum over the possible partition of this excitation. And then I need to insert three vacuums. So my seams are completely empty, and I just glue them back together as is. And this is valid up to 3 level and 1 loop. When I go to 2 loops, I see that actually I can have, since the length of this bridge is 1, I can have 1 mirror particle inserted, and this will be the first contribution that appears. Then if I go to 3 loops, I will see that beyond this contribution expanded to the next order, I will also have 2 contributions coming from the left and the right seam. So the idea is this: you take your hexagon, you dress it up with different mirror particles that live in all these different seams, and then you glue them back together and see what happens. Very well. How does this integral look like? Well, if you ever looked at any integrable, if you've ever done any integrability of any sort, the idea is practically, okay, I need to sum of all the possible flavors of this mirror particle that I insert. Okay, what it will do? Well, this particle will interact with my mirror particle that will traverse this hexagon, and the same will happen on the other hexagons, on the left and the right hexagon. This will give me some sort of interaction that will appear with these S matrices, which I know of because I know how they look like. And the idea is that now I need to take this sum. And what this sum does practically, it gives me something which is known as a transfer matrices. So if you want differently, the idea is that this mirror particle acts as a probe, and this probe needs to interact with all the possible physical excitation that are in my non-BPS state. And to do this, the only thing that it can do is that practically interact with them with a series of S matrices, and then I need to trace over the fact that I'm closing down the two hexagons together. So this is not unexpected. This is actually what you would expect. And okay, just for completeness, this is like an SU2/2 transfer matrices. This is only for people who know a bit of N equal 4. But anyway, and of course, the other thing is that I'm inserting one excitation here, but my physical excitation are here. So what I need to do is that I need to analytically continue the excitation next to the physical sheet, and then okay, this will give me okay. Anyway, the idea is that the transfer matrix, which actually encodes the dynamics of my integrable system, appears when I studied how this mirror particle interact with this with the physical ones. Okay, now you go to for loops and you start having problems, and the problems are the fact that you get, as I mentioned, these finite volume effects. What they are? Well, simply is the fact that now you can insert one on the left and on the right two mirror particles. But of course, there is clearly a pole if the energy, or if the value of u is equal to v. Okay, and this gives you some divergence, which then you need to cure. Okay, and you can do this. Practically, what you can do is that you can deform the contour, and then you can write some practically one contact term that acts in this way. And you're like, okay, perfect. I've fixed this problem at for loops. Maybe, I can hopefully try to fix the problem at also tire loops. But actually, it becomes way, way worse. Like you get many more of these poles, many more of these things. And, a systematic treatment is, you need to find a systematic treatment. Otherwise, you're overflown by all these divergences and you don't really know what to do. And all the picture that we had goes to the trash because we can never use it. So what we did was practically, okay, let us try and see. I mean, we have perturbation theory up to 5 loops. Let us see up to 5 loops how much we can infer from all these possible divergences, and if we can come up with some sort of way of correcting this asymptotic hexagon, so hexagon that works for this very large state, for also shorter operators. And our idea was, okay, I mean, I have what I can think of is that this wrapping effects can be seen as a sort of renormalization of the physical state that lives on the top of this hexagon. And I can then think, okay, what I'm trying to do is practically, I have this asymptotic picture. We'll have these transfer matrices for this this asymptotic transfer matrices. Maybe this is not the correct object to actually encapsulate all the dynamics, because there are effects for which, I can, as I mentioned, you can generate particles that they can wrap around this surface. And I need somehow to find a way to actually describe them. Very well, so you can think of this, and we did it. So we found a way to practically write some sort of non-perturbative version of the integrand that accounts for all this wrapping correction. And this worked very fine for the left and the right. But now you're trying to look at the bottom, which is the one where I insert a mirror particle here, and you see that one picture fits with what we want, but then there is a weird new effect that we had to understand. And I think that fit nicely and explain also some other misunderstanding in the literature was the fact that actually in the bottom bridge there are 2 different type of, if you want, waves. There is one which is exactly what you would expect, and there is one which is actually has a different, the exponential is negative in this case. So this is suppressed at weak coupling, so you will not see it from up to 5 loops. And this represents practically another type of excitation that you can have on the bottom bridge. So what I'm trying to say is practically that while on the left and right you can use what are known as non-compact transfer matrices, for the bottom one, since you have 2 copies of these 2 non-compact objects, you end up needing to use a compact representation for the transfer matrices. The idea is that this piece was missed, and this is actually what we found by doing this by checking at 5 loops. So, okay, to put everything together, what we can do now is that we can use building blocks from the QSC, so this fantastic non-perturbative mathematical tool, and the QSC gives you also these transfer matrices. And what we have done is that we could write these different building blocks for your integrand of your hexagons in terms of these non-perturbative objects. So in principle, this, if it's correct, gives you a way of constructing hexagons and computing structure constant to whatever loop order you want, given the caveat that you need to compute this integral. So coming to before, integrability gives you an answer, but then you need to be good at doing integrals, otherwise the answer is pointless. And yeah. At the beginning, I don't know if I was very clear, there's these 3 different integrals. When I'm gluing back, you need to integrate over the mirror, and so it's not super easy. And okay, very well. So let me just skim to some weak coupling tests that we did. So okay, as I mentioned, there was this 5-loop computation, and we were thinking, okay, can we match this with now our new and very powerful ansatz? And the answer is yes. So you actually look at some ratio in such a way that you can probe only this particular object. That is a bit simpler than the rest because, of course, there are complications everywhere. And you can looking at the QSC. Okay, this is a bit technical, but the idea is that you can write actually an integrand for this object is a bunch of eta functions. These eta functions are, I don't know if anybody have ever heard Euler-Zagier sums. It's like some different version of Euler-Zagier sums, or if you want, polygammas. And what you can do is that you can take this integral, you can take it by residues, and okay, you close the contour on the upper half plane, you take all the possible residues, that here you have u minus ia over 2, you take all of the residues, you sum over a, and what you get is that, fantastic, you can actually compute directly this in terms of zeta values, and you see that this, if I take the length of the bridge, so if I take the weak contraction between the 2 operators at the bottom to be equal to only 1, I see that actually I match perfectly with what is respect to perturbation theory. But now, having done this in an integrable fashion, I can actually extend this to whatever length of LB I want. And okay, these are coupled, but I mean, you can go as high as you want practically. And you see this will come into play practically at 6 loops, 7 loops. Now you can do whatever you want. This, of course, is only one part of the answer. There's still all the rest. But I mean, this gives us good hope that what we've written is actually correct. Of course, now, yeah. Yeah, in principle, yes. But this up to 5 loops, yeah. Yeah, yeah. Yeah, I mean, if someone is crazy enough, good for them. I think nobody will try to do 6 loops, but yeah. I mean, this is also for a ratio of 2 structure constant. It's not exactly the full structure constant. So because the other pieces are a bit complicated, you need to take some contour integrals over some specific like it's a bit more involved. But let me say this is the easy piece that you can study to very high loop order. Okay, now there has to be also some fantastic. Now I'm gonna end in time. There has to be also some holographic test. And okay, what do? You now take your operator, you scale them as as the length, the spin, and the dimension of this operator scales as the square root of lambda. You have an holographic picture. You can compute this using integrability. Okay, moral of the story. From classical integrability computation, you will see that you would have 2 contributions. And this second contribution was a bit mysterious. But from our representation, since we have this SU4,4, this actually fits perfectly into play. So practically, our bottom bridge does exactly what you expect. So it gives you this second bit that you would not get otherwise. Very well. To recap, so what I've tried to explain is that there is this nice conjecture for computing structure constant, the hexagons. It was written with all these infinities, but we found a way to use them or tame them by using tools coming from the quantum spectral curve. As I mentioned, we had 2 different tests. One was the weak coupling test, which was done towards this perturbative computation. The other one is this holographic test, where we check that the expectation is exactly the same one as you would have from purely you have this worldsheet integrability, and you compute the structure constant, and you see that the two match perfectly. Okay. Now let me go to the new stuff. I'll be very brief. What else can we do? Now we have this thing, which in principle is non-perturbative. We can do whatever we want with it, with limitations. And can we study other regimes? Well, the answer is yes. We can study a very nice regime that also has been studied in the QSC, which is this spin goes to 0 limit. So practically, the idea is that you take your non-BPS operator and you somehow expand it close to the BPS point. This, of course, I would not know how to write this operator in this limit. I think this is some sort of a non-local complicated object, but I can do this at the level of the QSC very simply. I can construct again the WB, and we did some tests, and this is all very technical. The idea that I want to say is that we expanded in the small spin limit. We looked again on the same quantity, and comparing it with some perturbative computation, which are, I want to stress, way more complicated, because what you need to do is that you need to compute the same structure constant or the same object from hexagons, so using like the hexagons at finite spin, and then you need to compute it for a very large set of spin, and then you need to interpolate them using harmonic sums as your basis, and then you need to find some sort of find these functions that give you practically the value for each value of S, and then you need to take the small spin limit. So this can be done up to 3 loops, then up to 4 is like too complicated. And the nice thing is that it matches, but now it's super nice because now we can take our small spin representation and use it directly to compute these things. We don't have to pass through all of this check. Okay, what else have we done? Well, we can do many more things at small spin, as I don't have much time to explain them, but the idea is that we can take all our hexagons, except the normalization, expand them in the small spin limit, and compute this thing to whatever loop order you want, because these formulas are super nice. They're very reminiscent of something that comes from, if you want, localization. There is a lot of nice mathematical structure. The best thing is that actually we can also compute them as strong coupling. We need to use numerics for some very technical reasons, but we were able to do it. And so we were able to construct the 1 over g cube corrections to this small spin hexagon, okay? And using 2 different regimes, so using the semi-classical regime and the small spin regime, we were able actually to finally access the strong coupling limit of the structure constant. And we were able to extract the structure constants up to some 2-loop order in this stringy regime. And this was not done before, and it's very nice that now we're also able to push the hexagons not only at weak coupling, but also at this strong coupling regime. Okay, going through the small spin, so this big like caveat, otherwise it becomes too complicated. So the next step, hopefully, will be to try and see if we can push to higher order in S and see how much we can still extract from this formalism. Okay, let me conclude. So hopefully, I managed to present our conjecture for these hexagons, how to treat these divergences that appear when you try and glue back these two objects. I hopefully convinced you that what we did is more or less correct. At least that's what the tests tell us. And I also tried to show a bit that now that you have this conjecture, you can expand it in different regimes using the fact that it's written in terms of QSC building blocks. And the idea is that the first regime you want to look at is this small spin. And we were very lucky that with this small spin plus this classical stringy, if you want, classical string limit, we were able to actually fix the strong coupling structure constant from integrability, and it matches with what is expected from this ADS Virasoro Shapiro amplitude, and we can actually extend the results to different length of the bridges. Okay, of course, one will also like to see, can we tackle other regimes? Well, another one nice regime is this large spin regime, this JKP string. It's very interesting, but of course, there are complications there because your integrants of the hexagon scale is u to the s. So if you take s to be really, really large, what does happen? This thing diverges. So you need to be able to compute these integrals in some way. And the hope for the future is that all these complicated, multiple integrals, multiple products, multiple sums, hopefully can be, simplified in a different sort of mathematical framework. Something like, I don't know if you've ever heard of it, this Fredholm determinant. So the hope is that you could represent all of these things as some sort of ratio of Fredholm determinants, or maybe similar object to this. Anyway, with this, I conclude. Thank you.
So are there any more questions? There are many questions. So
Very good, yeah.
You presented this hexagon construction by doing it loop by loop order, and it looks like it's a different translation of the Feynman rules eventually you're using to compute the amplitude. Where does integrability enter into this?
Very good question. So integrability enters because what I'm actually doing is that this single object actually contains like all your Feynman diagrams. So in some sort of sense, it's similar because you're doing perturbation theory. So there is some perturbative, is that the building block is like this gluing of 2 hexagons. So if you want, this is like your single Feynman diagram you need to compute, and this gives you already the full answer. So this is where what integrability buys you. The fact that you need to compute one thing, you don't need to compute an infinite number of them.
And how do you turn then this perturbative result into a full?
Yeah, so you do this practically. You take this, you build all of them. They all come about. this thing factorized nicely. So at the end, you can expand it in different order in G, and then you practically put it together and you re-expand in G. And okay, given this normalization that again you need to compute, it's not yeah, okay. This is like the more annoying bit. This is some sort of determinant that gives you okay. Anyway, split at this, you take all of this, you re-expand it in G, and then it's just a sum of all the different contribution. So you have this, what is known as this asymptotic contribution. So this is the empty hexagon. This is what usually you call asymptotic. Is how you practically split the roots that you have, and this you can do. It's again, that's annoying, but you can do it. This is like the first integral that comes about with this integration, this transfer matrices, and these are also integrals of the transfer matrices. The point is that while this one doesn't have any poles at physical roots, this one do have poles at physical roots, so they're very annoying because at the end of the day, these poles need to cancel, but they don't do automatically. So you need to, when you put everything together. So let me say, for the bottom, we have everything more or less under control. For this one, there are some technicalities that still need to be resolved in how you do this computation. It's similar. It's just that I think the single hexagon will more or less be your single form factor if you want. Like, so this is like, yeah, gluing them together, and then, I mean, practically also to do this normalization, we use this Leclerc-Musardo formula. I don't know if you've ever heard of it. It's like some way, I mean, okay, we had to extend it because that works for diagonal for a Abelian object. This is not, there was some complication, but at the end we were able to practically see. So at first you see that this works for the two adjacent, so the left and the right. And this was written also before us. I mean, this well known. The problem was this bottom. We didn't know what was happening. Then there was the perturbative computation. We saw that there is this extra bit, and one needs to then put it into some theoretical framework. And the idea was exactly this, which now it seems trivial because I mean, if you see it works. But yeah, that was the complication.
Imagine that you want to go a little bit non-plan. Take the first correction where integrability is lost. But can you imagine, is there some work where integrability still helps organizing your perturbation theory?
Yeah, so as I was saying at some point, actually, you can use the hexagon to tessellate the non-planar surfaces. It's not easy. It's very complicated. I mean, there are papers by Pedro and other people that do this. It's extremely difficult, especially because you need to understand how the different tessellation work and how to glue them back together because you have this non-planarity. In principle, I think they were able to do it for 3 level and 1 loop. I don't know. It's very, very, you know, this is the simple setup you can do. In this, we understand the most. If you move a bit around, there are some good hints, but we still need to. So the hope is that we can find a better representation for this hexagon in such a way that then we can, you know, use it in an easier way. So the hope is that we are able to, by looking at small spin and by looking at different things, we're able to write things in a more, which is like SOV, which is this separation of variables. So it's a way that looks more like you're computing some sort of scalar products of some states. So this is what you would like to have because this is like a nicer object to study than this. This is like super complicated. I mean, this thing is like awful. It's like you're expanding a random determinant. Literally, this is like you look at it and you look. I mean, it's awful. So it's very cumbersome. So once we do that, then we're able also to tackle the problem that you want to tackle with this 1/n probably easier. I don't know how much it will take us. Also, I mean, 2 spinning and 1 non-spinning, super complicated. I think they can do like 2 loops or 1 loop even. So not SL2. I think there was some results in SU2, but that's it. So I mean.
So Alessandro, if I understood okay, you presented this hexagon proposal, yes, for computing structure constants of 2 BPS and 1 non-BPS. And you mentioned that this proposal had problems with divergences. So did your work cure those completely? I wanted to clarify this. Or there are still, so is it now complete? Can one say that there is a complete prescription for these 2 BPS, 1 non-BPS structure constants that is free of divergences or not?
Yeah, so what you need to do is that, so first you need to correct this propagator. You need to shift the contour of the propagator. And then you need to use the integrands that we give you, which are this one given in terms of the QSC building blocks. Once you do that, then in principle, this is correct. Like this is what you need to do. Of course, again, integrability gives you something. You still need to do the integrals, and sometimes,
I'm just
yeah.
trying to understand
Yeah.
principle or
Yeah, no.
anything is missing.
So.
And okay, this actually takes me to the second part of my question, which was, okay, you were able to make a newer proposal or refine the previous proposal that cures these divergences, mainly by looking at the perturbative data? Are there physical motivations why this object should be related to the transfer matrix of the spectral curve as such, or is it purely empirical based on the perturbative data that you were fitting or comparing it, or reverse engineering?
Yeah. So if you I mean, I think that. So there are a lot of things in the middle because T functions are like the last step that you want. There are first like this Y function, and people have figured out how to do the left and right in terms of this Y function. Actually, that's what we use to rewrite in terms of T function. So that is more or less understood. The physics behind it is understood because the Y function have a clear like physical interpretation. So you can think of them. My understanding is mostly that the transfer matrix tells you how like a probe particle interacts with all your state. No, so you're inserting a resolution of the identity. So you're setting like particle, multi-particle, all this set of things. And of course, if this is large enough, I can only use the bi-Z-test matrix. So this thing interact. There is no wrapping effect. So I can just use this asymptotic transfer matrices, and that's exactly what you find. Okay. But of course, if things are shrinking, then you will have these wrapping effects. And what gives you the solution to the problem of computing transfer matrices in the case with the full S matrix is actually the QSC. So in some sort of sense, I think in retrospect, in retrospect, it makes sense that this is the object that you will need to use. It's also very nice because I didn't explain it, but I mean, these things actually depends on some hexagon form, like some hexagon generating function. But all of this is encapsulated already in the QSC. So the QSC already directly gives you these objects. So it's something like it knew already that this was the correct thing to do, or I mean, this is one of the things you could do. So yeah.
Sandro, I would expect that in a large spin limit you would have some kind of semi-classical approximation that you would be able to give you some results in closed form. Is it correct?
Yeah. So I think what you refer to is, I think you. Yeah, no, exactly. So I think you could do GKP strings, right? This is so usually I think we expand in terms of BMN vacua. So all of our things are BMN, but of course you can also do GKP. Like I mean, you probably could build an hexagon with GKPs, and then you can try and do it. I don't know if this.
I really want some semi-classical approximation of string that is.
I think no, maybe you're right. Maybe there is also that. I mean, I think there was a paper recently by Kravchuk and some other people where they computed spiky strings, like there's n spiky strings. I think probably there is some connection. From our perspective, it's a bit more difficult because, as I said, this thing grows as u to the s. So if you take s large, this is going to be awful and clearly not.
The second very strict question. So far it is in the SL2 shape.
Yeah.
Is it only that says okay to go to the SL2, for example?
So there is
problems of generalizing
that you want the left-right symmetry. So a little bit technical. What you want is that in some sort of sense, you want the left and the right to be two copies of the same thing. But this is not. I mean, we believe this to be true. So we believe the things that are not left-right symmetric should be automatically. There's like a selection rule for the things that are not left-right symmetric are automatically 0. But we don't know if this is true. I mean, you would need, I think, to do some computation and check. But in principle, you can also have like these T-hooks that are not symmetric, and that would give you problems because I think all our ansatz works for the fact that left and right are practically the same. They're just related, but some shifting of some bridge. So no, this fixed the WB for the WB. So the WB is written in these terms of this compact representations. But this left and right live on the fact that this thing is it's symmetric. So yeah, this T matrix has this nice property that this is like symmetric. And of course, you can have states which are not, but maybe then those things are automatically selected to be. There has to be some weird thing that has to happen for which you will need to correct this thing. But also, if you want to do spinning operators, this need to be corrected if there's more than one, because then there's no notion of bottom bridge, right? Because two operator needs to be renormalized, so it's a bit more complicated in that sense. But yeah.
Okay, so let's start like the afternoon session at 2:30 sharp because we need to finish like by 4 today. So we have to get out by 4.